Check 1, 2, check, 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 check. Check, check. Check, 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 1, 2, check, check, check. Check, check, 1, 2, check. Check, check, 1, 2, check, check, check. Yep, we see on the big screen here. Let me just give you a little bit more real estate up here. There we go. Can we do a quick sound check with your mic?
Hello, everyone. Hello.
Sounds good here? Yep.
Thanks. Hello. Hello.
You gotta leave your finger.
Okay. Person, and then
Good morning, everybody. We are starting day 2 of the Improving Scientific Software Conference. Today we have 2 tutorials. So really quick, just some logistical questions or things for the virtual audience. For this tutorial specifically, for the first half of the day, you can put your questions in the Zoom chat, no Slido, or you can ask them out loud. And that is for this morning tutorial. So if you have any questions, let me know. But otherwise, Shiquan, Junyi, I'll have you introduce yourselves and start the tutorial.
Good morning, everyone. I'm Shiquan Su. I'm a technical consultant engineer at Intel. I work for the One API department. Today, I will present the Intel Fortran compiler, IFX, and OpenMP.
Yeah, my name is Cheng from University of Colorado at Boulder. So I currently a research scientist. I was investing plasma transport in magnetic confined devices such as ITER. So currently we have a simulation called Cheng. So it's and to simulate the transport in it tokamak, devices. And currently was Shiquan and also some other colleagues from Intel and also other institute helping me to optimize Gen code on Intel machines. So I'm here to help Shiquan to present an example of this my current code and also give him some support for this tutorial.
So let's start our today's tutorial. The topic of today's tutorial is OpenMP offload to GPU and Intel Fortran compiler IFX. We have two parts. In the first part, we will go over the update of the Fortran compiler and the base introduction of the OpenMP offload to Intel GPU. And in the second part, we will show several case study, including the plasma physics simulation called GEM, and also another user case of offload the MKL core solving a large linear matrix on PVC. So let's start from the part one. So here is the brief introduction of the Intel compiler IFX. So Intel compiler, Fortran compiler IFX sit inside the Intel One API developer toolkits. Here is the release schedule. Usually we have 3 major release every year, usually at April, July, and November. And at the November, we will release the One API release for the next year. So the 0.0 for the year in the number actually come out the year before. And now we just released the 2024.1. It's publicly available. You can get it from the Intel website. And the next major release will be around middle of July. And then we will have the 2025.0 near the end of the 2024. So for the 2024, One API 2024, one of the main news about Fortran compiler is we announced the application notice for i4, Intel Fortran compiler classic. So, and it's officially deprecated. And when you invoke the i4 compiler now, you will get a warning to remind you to start the migration to IFX. And it will be still in the package, probably till the end of the 2024. And then it will not show up in the 2025 product. And somehow, if you know where to find, you still can find it. But then the i4 will just step into the fade away process. So now it is the good time, best time to start the migration to IFX. So we recommend the customers to transition to use the LLVM-based Intel Fortran compiler IFX. So the IFX is the LLVM-based, which is the mainstream popular Fortran compiler now. The compiler technique now at LLVM compared to GNU. The LLVM provide much more flexibility, much more better user experience, lots of compiler tools to support your research. So for more information on IFX, please visit the websites, and the slides will be available after the tutorial. So here is the recap of the roadmap of our transition. So the upper side is about the i4. As you can see, it will be we move from the toolkits in around the 2024 and 2025 timeframe, and then we will roll into the legacy product support model. So we still recognize that there's a market need there to support the legacy product. So we have another type of support called legacy product support. It will mainly basically it will mainly handle the license and the installation issue. So basically, if you pay the service, if you pay the support, you will get a way to download and license the product. But we fade away the customers. We fade away the technical support and the feature requests. Those type of support. So and the lower part is about the IFX, and the IFX reached the production quality at the second half of the 2023, and the IFX support both CPU and GPU, and there's no native kernel programming language support for Fortran at this moment. So for a long time, the Fortran user have no native way, directive way to program on GPU. The previous approach mainly rely on interlanguage calling, go through a portal calling a C interface and then go into the territory of C++, CUDA, SQL. And now at this moment, we have a better solution for that. So it's 2 layers. So for the first layers, the IFX fully support the Fortran 18 specification. In this specification, the interlanguage calling portal procedure become much more standard. So now you can find those clear definition of how you do interlanguage calling in the Fortran specification, latest specification. So this will keep your legacy, keep your original investment work in good shape. So whenever you make your effort to do the interlanguage calling, to do the calling C, to use the CUDA, to use the GPU, that will still work. And the second layer is we provide 2 native approach for the Fortran users for using the GPU. One is the OpenMP programming model. The OpenMP programming model have long history supporting CPU. Let's call it OpenMP CPU threading. That is the existing specification for more than 20 years. And on top of that, now we have the OpenMP offload, or we can call it OpenMP target. That is the new section, like a quarter of the current specification. That part will allow the programmers to use a target device. And the target device can be GPU, can be other new type of accelerator. And the IFX support the OpenMP target, OpenMP device specification, so that can run on the GPU natively. And the good thing is that OpenMP target, OpenMP device is like a subset of the overall OpenMP specification. So whatever other part in the specification about the data management, about the CPU threading, all those, they will coexist. They will be compatible with IFX OpenMP offload. And we can see that that will give a user a much better, much integrated user experience for the Fortran programmers, because your CPUs, your OpenMP CPU threading can coexist, can work side by side really well with the OpenMP target offload to device. And you can switch between them. You can go back and forth of them. You can have your code, part of your code one on GPU, part of code one on CPU, both using OpenMP, both accelerated by GPU cores by multi-CPU core threading, and that make the code really future-proof. And this is solid open standards, OpenMP specification, and the support across all major vendors, Intel, AMD, NVIDIA. So here is the definition of the deprecation and the legacy product support. You can read through it on the screen, and I will go past it fast. So, so here is some product highlight of the Intel Fortran compiler. So it supports OpenMP 5.x standards, and it can offload to Intel GPU from Fortran. And actually, I forget the second part of my statement. So there were two native ways to run Fortran on GPU. The first layer is that the OpenMP approach that we can treat that like the Fortran is a base language, like the C and C++ a base language, and the OpenMP programming model is a language add-on to your base language. It's an add-on to your base language specification. So obviously we can go through the add-on to use the add-on specification, OpenMP specification to take the advantage of GPU, of the accelerator. But on the other side, for the base language, for the Fortran, it has its own specification. For the Fortran specification, now for the latest, for the new Fortran specification after 2018, the do concurrent also it's GPU aware. We can also auto offload the base language do concurrent features to GPU natively. So that open up more paths for the Fortran programmers to use the accelerators. So in this case, the accelerator programming will become transparent for the Fortran programmers. So you don't need to think about the accelerator. You don't need to think about all the hardware details. The only thing you require to do is follow the base language, the Fortran base language specification 2018 to program your code in the sense that you write a do concurrent loop, and the do concurrent loop follow the syntax, follow the specification requirement. And after, if your loop has the features comply the do concurrent requirement, then on the compiler level, on the compile time, we can turn on the flag and instruct the compiler to generate another set of binary, another set of executable, which can be executed on GPU. So it will be the same programming experience, will be the same source code to the programmers, except you only need to turn on the compiler flag. And you can turn the compiler flag on and off source file base in your whole application. So it let you to accelerate your code in an incremental way, in an iterative way. So, this is the product highlight of the IFX. Basically, we focus on protect your Fortran investment. So make sure your current production code, your heavily invest human effort code can transfer to IFX seamlessly, and also take the advantage of the Intel PVC GPU. So here is the structure of the Fortran compiler, Intel Fortran compiler. So we have the front end and the back end of the compiler. So for the front end, basically it's a set of tools to perform the lexical analysis, syntax analysis, and then a semantic analysis. And then in that case, it will generate a semi machine code is still human readable. It's called IR, intermediate representation. And in those, for those IR, and then now we have two ways to generate the IR. The I4 will go through the traditional way, generate the IR that we will feed into the I4 backend, the level 0 Intel level 0 backend to perform the intermediate code gen and the code optimization and then the code generation, the binary generation. And for the IFX path, it will go through the LLVM backend and generate the IFX LLVM binary. So basically, it's the IFX has the same front end and the runtime library as I4, and then with the modern LLVM backend compiler technology. So here is some high-level understanding of IFX. So you can read from the screen. Basically, the key takeaway is the optimization, vectorization, optimization reports, inlining, unrolling, inter-procedure optimization, and profiling guide optimization. All these will be in the IFX. And one of the most important optimization flag you can use is the -X host. That will help you to pick up whatever the latest instruction set on the Intel compiler. And basically, it's very, usually it will accelerate the code with the fast math. And if you need more precision on your code, you use the floating point model precise. So here is some common optimization compiler flag. Basically, we try to keep the similar user experience like the I4. So you will see lots of them very similar to I4. And the one of the important is the IPO, inter-procedure optimization. So for the IFX, we emphasize the IPO a lot. So the IPO can give you another layer of optimization, which let you optimize the code across source code files, across different compilation unit, which is super useful if you're handling a large code set, like your production code, like WAR. Because now you explore more optimization opportunity across different modules, different files. So here is those performance option. It's still pretty similar to the I4. Basically, the main thing we recommend is try out that -X host. So let the compiler to pick up the best instruction set for you in the compiler. So and also try to do the IPO, inter-procedure optimization. So here we talk about there was some OpenMP stuff by the IFX heavily support the OpenMP and OpenMP offload. So the -Q OpenMP -SIMD is on by default, and the other I4 flags are accepted quietly without message. And in our I4 deprecation period, we will generate a warning 10148, let you know that you need to pay attention to the deprecation of I4. And then we provide a diagnostic flag called -Q next gen -diag. In that case, it helps you for the I4 to IFX migration on the compiler level, because in your I4 implementation, in your I4 makefile, probably you apply a lot of Fortran compiler flag here and there for your different need. And those compiler flag, most of them already translate transfer to IFX in the meaningful way, but always, because there are hundreds of flags, always there's still a working front end that we are doing the transition. So through this flag, you can check which compiler flag is latest supported and which compiler flag will be supported in the future. So basically, when you use IFX, if you think one of your compiler flag is not working, run this command and check the both lists to see if it is already support or if it's on the roadmap to be support in the next few release. So that they will give you the sense, they will give you the timeline, what to expect in your i4 to IFX migration. So here basically is also about the architecture optimization. So it's a explicit example of -X host. The compiler should be smart enough to pick up the host architecture of your CPU. Our latest generation is a Sapphire Rapid. So basically, the -X host should already do the job to pick the Sapphire Rapid instruction set for you. But somehow, if there was some environment set up, your system admin set up the machine in a different way, that the compiler does not have the hints from your operation system to find the host architecture, you can explicitly say -X Sapphire Rapids. That will enforce the Sapphire Rapid instruction set from the compiler. So also for the AVX 512 vectorization, IFX also have support and it provides the following flags. You can read it on the screen, and it's the same as the i4 compiler flag of about the ZMM. Because you have the same size of your register files space. So if you put a longer vectorization width, then you kind of each operation get smaller register file space. So basically, this flag is controlling how you want to operate the register space. You want a wider vector width with smaller registers file space, or you want a shorter vector width but with larger register file space. That will affect your computational kernel a little bit. But usually you only have two choices. You either choose a larger one or a smaller one. It's worth to just test it out. So also for the optimization report, currently we only support the report level from 1 to 3, which will give you different layers of verbals of the optimization. And we are still under development to provide you the same flag from the i4 about the report phase. So currently, just assume that IFX will give you all the phase, loop, vec, pal, or at this moment. So also now the optimization report come in two formats. One is the normal OPT, RPT file. The other format is the YAML file. The YAML file can be you can view the YAML file optimization report by the Python tools provided by LLVM. So this page talk about the IPO interprocedure optimization. So basically, with the IPO, the compiler will try to optimize all the files at one time. so the optimization can go across the source file boundary. So here is some other good things to know. Probably you can read it on the page quick. And one of the major difference we want to point out is for the IFX now, we only create 64-bit binaries. We do not accept the 32-bit anymore. So there are some known issue is for the IFX in some type of complex data performance, we kind of downgrade it a little bit because we don't have the native support for those low position. So all the low position implementation will convert to the default precision, and the default precision is longer. So usually give you a little bit performance penalty. So this page is for the OpenMP implementation inside the IFX. So we support all the OpenMP 4.5 now, and we support most of the 5.0 and 5.1, and most of the 5.2. So actually, this slide is a little bit old. Now I think we can also say that we support most of the OpenMP 5.2, and there were more exciting OpenMP features coming. Probably by the end of 2024, like November, December, that will be the time the OpenMP 6.0 comes out. One of the most important features in the 6.0 is the interop. Because currently we only do dispatch, which means if we want to call a function call from a library, that library needs to have OpenMP variant. And then we dispatch the call to that variant. And if that variant is not available, the compiler silently, the one-time silently fall back to the CPU version. So we need a source code implementation of that function call on the GPU, OpenMP GPU exists there to do the dispatch. But for the interop, that can be done on the binary level. We can interop with existing accelerated binary through the OpenMP programming model. So this is the above is the introduction of the Intel IFX compiler update. Next, let's talk about the Intel data center GPU architecture. This is a very brief overview. Basically, try to look at the GPU architecture from the OpenMP angle, because you have so many ways to look at the GPU architecture. Probably, if you are doing AI, you see the GPU architecture in a different way. So for OpenMP, in the OpenMP view to see the GPU architecture, there was three important layer of concept. The first one, the smallest one, is execution unit. It's EU. On the EU, it is where you run your thread, one thread at a time. That's how you process your thread. And on the Intel hardware, so actually we have multiple generation of GPU. So what I show you on the screen here is for the HPC style. For the early generation, we have another generation which have a similar concept, but the terminology is a little bit different, and that one is more hybrid between HPC and AI. So let's focus on this set of terminology. So for this set of terminology, the EU is our XELP execution unit, and the second layer is a group of EU. When you have a group of EU, here we call it subslice. It's similar to the OpenACC concept of your vector. And here it's where a group of EU work together. And this is this is very this is set, this is fixed in whenever you design your hardware, whenever you pick up your hardware structure. So in the subslice, in this level, all the EU, which means all the threads you are running at the same time, they see the same local share memory, which is your fastest memory. So you have the memory coherence here. And for the EU work together, you get the concurrency. So if the threads in the same subslice running at the same on the different EU, you can guarantee them see the same memory and execute at the same time. And these are the subslice is one of the most important concepts in the OpenMP and the OpenACC comparison. And this is the major architecture difference between the Intel and the NVIDIA and also AMD. It's usually the Intel have a smaller size of subslice compared to the counterpart concept of NVIDIA, but we put more subslice on your device compared to the NVIDIA structure. So there's pros and cons on two different architectures. Probably we'll go later. And then the third layer, the third level, the highest level in the architecture is the device. The device is a group of subslice. And you can, basically it's your kernel, it's your grid, it's your OpenMP target region, it's your OpenACC region. So here it's you basically inside your kernel you want a group of subslice work for you, and you divide your work among different subslice. So pay attention to the concept of device here. This is an abstract software concept. You send your kernel to your device, but this device, it can be a whole GPU, half of the GPU, a subset of the GPU by how you organize your accelerators. And the device concept is important that it connect back to your CPU with the core, with your MPI rank. Because usually you want one MPI rank on one CPU core and then operate data mapping to one device. And that one device, it's an abstract concept. It's a group of subslice. It can be a whole GPU. It can be half of the GPU. It can be a tile. Because for the Intel GPU, it's like the CPU, we have two sockets. For the Intel GPU, we have like two tiles at least. So most of the time you don't, your kernels don't use the full GPU on Intel. You use a tile of the GPU of the Intel device. So in that case, we call a tile the device. So here is the details about the concept I introduced before. So we start from the lowest one, the EU. So each EU is it's the counterpart concept with the SMT in the NVIDIA structure. But the twist here is our because we have fewer EU in each subslice, so on each EU we handle more threads than the NVIDIA structure. So basically, we probably still have a roughly similar, a little bit smaller number of totally threads we can handle on the inside one subslice compared to the counterpart concept on the NVIDIA structure. But because we have even fewer number of EU, so for the concurrency for the SIMD, we have even a shorter width, smaller, narrower width, because it's usually it's easy for the NVIDIA to perform like 128 vector width, 128 thread work at the same time on the subslice. But for the Intel structure, we usually only support 16 or 32 width. But we have more threads in a different stage in the pipeline ready to swap between the. So overall, each subslice can handle a roughly similar value of threads compared to the NVIDIA structure. But we just have, just in each subslice, each teams, each gang, this concept, sorry, each vector in the OpenACC concept, we have a narrower, smaller amount of SIMD width. So, and then we basically support two mode, either like 32 SIMD width or 16 SIMD width. And the difference between these two modes is you get half of the size of the register file space compared between them. So then usually that makes you a little bit, you need to make a little bit design decision when you form your kernel, how big you want your kernel to be. If your kernel is too large, it will overspill the register file space into the local memory, but it's not the end of the world. The code still works properly. You just need to swap the page more often. So for the next one is the concept of the subslice. So this is the where you get where is the largest range you can get the memory coherence. You see the same memory pictures. So so basically on one subslice you have 16 EUs in this configuration. So which means your SIMD width will be 16 here. And there's another configuration you can set up that it will let you see like 32 EUs. So in that case, your SIMD width is 32. But because in each EU it handles like 7 threads, so overall for the subslice it is still abstractly you're still seeing that 112 threads working together on your loop. So and then you put multiple subslice together to form your slice, and there are multiple ways to configure the on this hardware level. You can even put more slice to one GPU. You can put more slice to be one tile and put 2 tiles as one GPU. So this is the hardware level of the concept of the device. So and it's tunable. So basically you can view the GPU on your cluster. It's a group of subslice. The group of subslice. You can use it. You can participate in different ways. You can use it each tile or each slice or the whole GPU, because the whole GPU can usually have 2 tiles, and each tile usually have like 4 or 8 slices, and each slice have like 8 subslice. So, but all the concept of GPU, the whole GPU, tile, slice, they have no difference, but just an abstract concept of a group of subslice. And whenever you define a group of subslice work for you as a device, your MPI rank, your CPU core send the work to that device. So now let's go to the OpenMP GPU offload basics. So so we assume that you have the basic knowledge of using the OpenMP with Fortran. Basically, we will cover the one API overview and the OpenMP on the CPU review and the OpenMP offload, and then how to manage the data, device data, and how to express the parallelism. And then the OpenMP offload MKL. So why we want to use the one API environment? That is because we want to answer the programming challenge for the multiple architectures. So because our workflow grows with different type of data structure, like scalar, vector, spatial matrix. And we go through our programming firmware framework to land it on different architectures like CPU, GPU, FPGA, and other accelerators. And we can call it XPU. We want a software development framework that allow us to handle this in a uniform way to protect our investment. So you code in one source code, you code in one set of code, they should be able to run on all different types of accelerators, XPUs. So the one API provides the answers for these challenges. So basically, we abstract the layer of your CPU programming, GPU programming, FPGA programming into one uniform programming model, one API. So by programming through the one API programming model, you have the freedom to make your best choice of your hardware. You do not bound by one hardware vendors like NVIDIA. The one API programming model allows you to program in one source code, but the code can run on NVIDIA, AMD, Intel, different vendors' hardware. And so you can truly realize the value of your hardware investment, but you don't need to duplicate your software development effort. And also this can be future-proof because all the one API specification is based on open standard, open specification, and we evolve, we can combine to the latest open source specification development. So once you code with the one API, you keep compiling with the one API developer tools, your code is future-proof as long as all the open specification development. So for our product, we mainly have the different base language, C++, Fortran, Python, base language compiler. And then we have the add-ons like the OpenMP, like the SQL, one-time library. So that is the add-on for the base language. And then we also have all the performance libraries like MKL, like MPI, like 1DNN. And then we also have our vTune and advisor profiling tools. So here is the different structure of our one API toolkit product. We start from the base kits, and then we have the HPC kits, including our.
Sorry, you're not sharing your screen anymore. You might need to reshare.
So So basically, here is the menu of the structure of the one API package. So basically, for today's presentation, the relevant part is in the dark blue color. We have the Fortran and the C compilers, and we have the MPI libraries, and then we have those vTool and advisor tools. So let's get a quick overview of the OpenMP on CPU. So OpenMP is a cross-platform standard supporting shared memory, multi-processing programming. So here is the history. So the OpenMP journey start way early, basically back to 1997. Basically start from Fortran, and we want to take the advantage of the multi-core infrastructure on the CPU. And it has so many development up to OpenMP 4.0, which is still like 10 years ago, 2013, we start to support the accelerators. And nowadays, 2024, we are looking for the 4.0 with the major improvement of single device usage. So the structure of the OpenMP programming model is basically we utilize the parallel construct. So we put that PEMA. So here we use a C example, but the syntax are very similar between C and Fortran. So for this simple case, I think we can do the translation in our head to basically examine the OpenMP programming model in either base language. So we put the PEMA OMP parallel outside our loop. In this case, we will start a parallel region, and then we launch a team of threads. And the important concept here is the team. We will have a similar concept at the OpenMP offload. And then each thread will execute the same code redundantly. And then we want to distribute the work because we don't want each thread run all the same code. We want each thread one part of the code, and then they combine together, run the whole code. So in that case, we need to use the PEMA OMP4. So now we can see there are two layer difference here. The first layer is the parallel. The second layer, the OMP parallel. The second layer is the OMP4. They be responsible to create multiple threads, and then the second layer be responsible to divide the work, basically the work share. So this is the concept of the OpenMP parallel. So we can take a quick look of these basic examples, and you can also do the reduction after the parallel 4, and then we can also combine the two layer I just mentioned, the thread launching and the work share. These two steps, the parallel for the thread launching, the 4 for the work share. We can combine the parallel and the 4 in one construct parallel 4 to do the same thing. So this is an important concept of combined construct. We will see it later. So basically, if we don't want to go into so much detail and our code don't need to recognize those details, we can do the combined construct. We can combine the thread launching and the work share into the combined construct. And then we also can do the reduction. So other important OpenMP construct is like section, class, SIMD. Probably you will meet these construct here and there in your application already. So now let's go to the OpenMP offload, which means for the GPU. So the OpenMP offload using the GPU, we use a device model. For the device model, here is the important takeaway. The OpenMP 4.0 afterward supports the accelerator coprocessors as device. It's not GPU, not only GPU. And then the device model is one host, multiple accelerators of the same kind. Because for the one host is the CPU. On the CPU, you have so many cores. You have many cores, and you can use different cores to drive different GPU. That is the main idea. And you can also hybrid. You can, for example, you have 112. You have 120 cores on the CPU, and you have like 6 GPU connect to your host, and each GPU have 2 tiles. So you have like 12 tiles. You define each tile as a device. You can have your 12 out of 120 CPU core to drive 12 accelerator device to do the OpenMP offload, and hybrid to the OpenMP CPU threading. Your 12 MPI rank, your 12 core driving one GPU device each can also drive another 11 OpenMP thread on CPU for different part in your code. So in your code, in your current code, probably you keep using the 12 thread to drive 12 another. Oh, sorry, I do the wrong math. Another 9 OpenMP thread for each MPI rank. You can do that the same time as that 12 MPI rank drive one device on those multiple hardwares, accelerator hardware at the same time. You can hybrid like that. That is the beauty of this Intel IFX programming model. You really kind of like really easy to go back and forth on your large code base. You can test each loop case by case incrementally, which one's suitable to move to GPU, which one you want to keep on CPU. When you keep on CPU, you still can rely on CPU multi-threading, OpenMP multi-threading, set the OMP num thread to 10. You still have 10 ways parallel on each MPI rank, on each one MPI rank on your host. So for this device model, it's a host-centric model. So which means that basically we start our code on the host. Your input files, your I/O start on the host. Your data sit on your host memory. And then you do your data management to the device memory. And probably in the future, like probably not long in the future, that we can read the data into the GPU directly. So probably later you will be a chance that you switch to a device-centric programming model. And at that time, you only offload back the complicated logic kernel to CPU to get the fast clock speed, but you do your majority computational throughput through the device. But that is the future. Currently, we always stay with host-centric. And obviously, the memory space have the host and device, 2 different space. And then for the OpenMP programming model, we always want to map the data from the host to device, which means usually the data will be managed in a way that it has a host copy and a device copy. We don't explicitly say copy the data. That is kind of like easy to understand, because one of the standout OpenMP feature is your OpenMP implementation will always run on CPU without accelerator, or run on your hybrid system with CPU and GPU. If we explicitly copy the data by those OpenMP construct in your logic, in your code. If somehow your compiler does not understand OpenMP and ignore those data handlement, then you miss your data handlement. So in this sense, under this concept, we always do the data mapping, not the data movement or not the data copy in the OpenMP programming model. And so we have data construct to manage the data, and then we also have target construct to offload the code to the device. So here is how to evolve the offload compiler support. Basically, you need two flags. Obviously, the -q OpenMP that will enable the OpenMP support in the compiler. Basically, put the add-on to your base language. Right, the compiler basically put the add-on to your base language, the OpenMP add-on, but you need a second flag, the OMP targets equal to sphere 64 to enable the device offload. So the sphere 64, basically here you can understand it as the GPU, the Intel GPU, the Intel PVC GPU, Intel data center GPU, because the compiler backend, the binary format there is called sphere 64. It's basically, it's like the PTX in your NVIDIA language. So currently we only support the sphere 64 for the Fortran OpenMP offload. So there is the only value you can put for that flag. So the device construct mainly is the target. So you can see the different syntax, both C, C++, and Fortran on the screen. So basically, you use the target to signal the compiler that this is the code you want to offload to the device. And then after the target, you can put, the target is the highest level, is the construct level. So you say target, now you go to the device. And after that, you put in your clause. The clause is the second level under the first level, the target. So now you further tell the compiler what you want to do. You can tell him the device, which means which assume the programming environment recognize multiple devices. For this device clause, you will tell the code which device you want to run on. And but this is kind of like it's not that usual because I think in our case in the audience here we all work on large scale scientific application, and in this case you always have the MPI to help you to utilize multiple and probably it's a better way, an easier way to use multiple resources across different hardware. So in this case, usually you will set for each, you will let the MPI library to do the host device binding, let the MPI to handle what is the relationship, which core, which CPU core belongs to which MPI rank, connect to which device, and the MPI should handle that for you. And after the MPI does the host device binding, each host should only see one device. So in this case, even you put in the device clause, the device clause will only recognize the 0 value. It will only recognize the device 0. If you somehow put the device 1 there, then probably it will fail your code. And the next most important clause is the map. That is at the target level. And now when you try to use the GPU, now you want to handle the data mapping explicitly, then you will use the map. But for the OpenMP programming model, you are not necessary to handle the data mapping at your target region. you use the more recommended way is, the better way is you handle you form the data region across your whole program in a global level, which you use the structured data or unstructured data approach, which I will spend a lot of time to talk about that in the remaining section. And then also there's another small clause, it's called if. It's like it allows you to put in the logic here to fulfill some threshold to say it will send the code to the GPU or it will stay on the CPU. So this gives you another flexibility when you do when you incrementally set up your adapt your code to the device programming, because you can just change all your OMP target. You can just change all your OMP construct to OMP target construct, but you put in the if clause there, and then you set up your different level. It's like it's I don't know. Give some criteria. It's before 2024 or before shallow approach, something, shallow water approach, something. You can by set, you can devise your code in different sections that pick up the different criteria to offload to the device. So the execution model, the target construct transfer the control flow to the target device. The control flow transfer is sequential and synchronous. And so there were two important offload here. When we say offload, we have two parts. One is the control flow of transfer. The other is the data transfer. So the target mainly transfer the control flow. And for the data, we have many ways to do that through the map. So here is the simple example, SEPI. So basically, once you put in the OMP target, that part will become a target region. So for the device clause, you will have the target cause to transfer the control flow. And then you have the remaining, there are several other device clause related to the device. They are mainly about the data transfer. So the target construct is for the control flow transfer. All the others, the target data, target enter exit data, target update, they are for the data transfer. So it's really important that we have the concept here for the OpenMP. We have two types of transfer: the control flow transfer and the data transfer. For the control flow, we only need to have one construct, which is target, and all the remaining is for the data transfer. And the control flow transfer and the data transfer usually will be separate in your large code base. So if we want to call the function inside the target area, we need to use the construct declare target to put it in your subroutine. So here is some important environment variable in your compile time. So once you put all those OMP target treatment in implementation in your code, when you compile your code, you still have two options. You basically have three options. The most important option is the mandatory. In that case, if you enforce whatever code you have the OMP target run on the GPU. If we cannot find a GPU, if the device is not ready for any reason, it will fail. It will not fall back. So there you will make sure, because when you have running a large code, there's a lot of time you run into the trouble that it works, but it works with low performance, and you cannot tell if the code is run on GPU or is fall back to CPU, so it runs slower. So you use the mandatory variable here to enforce it run on GPU. And then you can say disable. So the disable will do the opposite, will enforce your code run on CPU. So that is the beauty of the OpenMP programming model. Is after you do all the migration, after you do convert your OpenMP CPU setting code to an OpenMP offload to GPU code, after you do all the conversion, you can start with the OMP target offload equal to disable. In that case, actually, the code will run exactly the same before your migration run on CPU. You can benchmark that performance. And then from that on, you can easily switch between mandatory and disable to put the code on CPU or on GPU. So keep your programming model, keep your programming practice very consistent. So basically, if you, after all these treatment, you don't need the original OpenMP anymore. You don't need to worry about you break your original OpenMP anymore. You basically you put the target after your original OpenMP to intend to offload, and then you have another handles, you have another knob during the compile time that you set it disable to put it back to CPU. So basically, once you migrate to OMP target programming model, it works both on CPU and GPU, and it works on CPU as is you previously on CPU. So for the offloading, we can also be asynchronous. In that case, we will put a clause no wait after the target construct. In that case, once the code offload to C, so once that region offload to GPU, the control flow of that region stay on GPU doing all the work there, but there's another control flow on the CPU keep going. The CPU code can go to the next section in your source code. So in that case, you can hide your latency. You can hide you can do host device acyclic execution. Sorry, it froze again. Yeah, so yeah, thanks. So this is the page for what I'm talking about, the async of loading. So in this case, you can keep the control flow proceed forward at the same time, both on device and host. And after the async execution, when you want to sync again, you put in the construct OMP task wait. In that case, it will make sure the host and the device back to the same line again. So we will make sure the host and device execution back to the same line of execution on your source code again. Okay, so now we go to the fun part. The most important part is the managing device data. So funny enough, this is the most funny part of the presentation. Is we tell you there were 6 ways to do to do this part, and it's very complicated. I don't want to say a word confusion. So the first way is you don't need to do anything. There's always a default behavior to help you to handle the host and device behavior. The data movement. There's a pros and cons here. The good thing is, so most of the time, it makes you only focus on those large array, large data set. For the other small variable, like the iteration variable I and J, most of the time, 99% of the time, it will do it correctly for you. You don't need to handle the data movement for every single variables in your kernel. This is the best part, the good part, but there's also a bad part. Worst part is this default behavior is very implementation dependent. And the vendors, the developers, we change our compilers behavior, default behaviors without telling you, and even without documentation. And we change back again in the next release, silently without telling you. So this is the current situation, the reality. So basically, the lessons we always want to keep in mind is we always need to have a mindset that there's a default behavior acting behind the scene. If you see some funny behavior, you need to think about that if it is because the change of the default behavior. So for example, for do a SAPI, for OMP target, we can just write the code like this. We don't need to do anything. There are still so many variables used in the target region. For example, like the I, like the array size, Y and X. If you think you need to handle the data management for every variable, that kind of freak out. Your code will be like 10 times longer in the big source code. But most of the time it works out of box. So the compiler is smart enough to identify whatever you need to put on the device and put it there. So the second part is use the map clause with the target region. So basically here, because we keep explaining that for the target is the highest level, is the construct level. When you put in the target construct, it signal the source code, they signal the compiler that the following section will be a device section. Put this part onto the device, which means you transfer your control flow to the device. This is the highest level construct, the highest level OpenMP operation, transfer the control flow. And within this construct, it also gives you an option to use the clause. The clause is the second level, is the one level lower than the construct. It's called the clause. It's you can put in the clause after your construct. One of the clause you can use for the target construct is the map, which means you signal the compiler under the target construct, transfer the control flow to the device. Under this, we also want to handle the data transfer at the same time. We do the map here. So the syntax of the map include the map, the clause keyword, and then the map type and the list of variables. So for the map type, there are majorly 4 different types: a log, to, from, and to from. You can read on the slides how what they means. So basically, here is the example of the SAPI. Even the code can do it for you correctly. You can also do it explicitly. In this case, your map, because the X is the input, so you want to map it from you want to map it to the device, and you don't need it back. So you only send the X from the host to device at the beginning of the target region, and you don't want to copy it back. And the Y is your output, and it probably has some initial value. So you need to send the Y to the device at the beginning, at the entry of your target region, and you want to copy it back. You want to copy it from the device at the exit of your target region. So the map type for the Y will be to from. So everything is intuitively and straightforward for the scalar and the static array. A little bit tricky is the dynamic allocate array. In this case, because for the dynamic allocatable array depend on implementation, but most of the implementation, when you declare that in your code, it only give you the it only registers your start address of that array in your memory. It does not have the full physical memory resources allocate to your allocatable array until you initialize it. But it's case by case, it's implementation dependent. Sometimes you can have some compiler flag to force that happen. But the point I want to make here is because we now during the code execution, we need to handle this host device situation. So for the mapping between host data and the device data for the allocatable array, we not only need a beginning, the starting point of your array, which is the first parameter, the start. We also need the size of your dynamic allocatable array. In that case, because we have the size information on the device, actually they will already allocate they will bookkeeping the size of your allocatable array on the device. So somehow it's still not fully subscribe the physical resources to that. That will cause problem. That will, if you transfer a lot of data to the device, they will make you overflow the page, the memory page on the device, which is really hard to debug in your code. But at least it has the requirement that you need to tell the code the size of your allocatable array. And pay attention to here is the second parameter is not the end. It's the length. That is important because we need to consider the situation that the array may not be one-dimensional array. It may be a two-dimensional array, something. So here is the same SAPI code, how we can do it. And so now we already finished two most basic data management method. The first one is do nothing. The second one is transfer your data right at the time you transfer your control flow. So now we go into the three and fourth approach, which is the most common use case for large application, is separate your control flow transfer and your data transfer. You do the data transfer once, and then you have multiple target region, use the same set of data on the GPU. When you do those target region, you only need to transfer the control flow. You don't need to transfer the data anymore because it's already been taken care of by the separate data transfer setup. So the first one is structured data. It's called target data region. Why it's important for the concept of structured data? What it means is for the structured data, the same data environment happen at the same compilation unit, the same source code file, the same subroutine, the same main program. In that case, at the beginning, before the entry of your target data region, you know how much data you want to transfer to the device, and you know how many data you want to get back when you exit that target data region. So that is structure. You have everything. You have all the idea at the beginning. So in this case, the construct is target data. And then you can use the map clause like in the previous target region. In the map clause, you already know what you will send to the device at the beginning, at the entry, and what will you get back at the exit of the target data region. So this will obviously give the better performance, give a better code management for your code because you know what you are doing exactly within the same compilation unit. For example, you are writing this subroutine, you're pretty sure you send the data to the device, the data is on the device. You do a computation, you get your data back. You are very sure it's structured. It's compared with the other called unstructured data, which means the data transfer happen at another subroutine. And probably your colleague, the guys at the next office wrote that subroutine. And you understand what he's doing. He's transfer the data for you, put it there at the device ready for you to write this subroutine. That will be the number 4. That will be the unstructured data. But now we talk about, we first focus on the structured data, which means we use the construct will be target data. This is on the construct level, and you can use the map clause. On the clause level, you can use the map, and that map will handle both the beginning, the entry, and the end, the exit, the data, how you map the data. So you know exactly what happened within this target data region. It stays in one source code. So the number 4 is the target enter exit data. This is for the unstructured data, which is that the construct is a target enter data or the target exit data. They can sit on different source code, and in this case, you don't know when you enter the data, you only take care how you send to the device. You don't care how you get it back from the device. So for the target enter data, when you do map, you can only do map. You can only do the to map type. You cannot do from, because you don't know when it will get back from the device. The same thing for the target exit data, you cannot do the to, you can only do from, because you don't know where the data is put it on the device. So here is the syntax. And there was another two uncommon use case, uncommon method to manage the data, which is called declare target. That is more like a global variable. If you know that piece of data will sit on the device forever, you can declare it at the beginning of the code. So they will sit on the device forever. The last one is unified shared memory. In this case, the OpenMP also provides you a way to do that by give you the API like the memory allocation call in C to explicitly allocate different type of shared memory. Okay, so I think, yeah, I think I overrun my time a little bit, so probably I will keep the last section to the when we come back from the break. Thank you.
All right, we're gonna start our 30-minute break, 10:30 to 11. Thank you.
My team managed over
All right. We're going to get started with the second half of this tutorial. So I guess I don't know if you want to, we can poll the audience if there are any questions from the first section. Feel free to just raise your hand if you do have a burning question for presenters. All right. Why don't you go ahead and take over, and we can ask again at the end before lunch.
Sure. Yeah. So in the second half, I will finish part one, and Junyi will talk about application case, and then I continue on the part two. So the remaining of the part one is about how to express parallelism on Intel GPU PVC via OpenMP. So this is a review of the architecture like we already discussed before, but now I put figures here, so give you some physical idea. So the most important concept is that subslice concept. It's where the subslice is always a group of EU, and that is the largest programmable unit. You have the memory coherence. You see the same memory image. So it depends on your different generation of your hardware, different generation of between different generation of your hardware, you will have the same setup, the same set of the same configuration of your subslice. So and that will host your teams. That will host your vector, the OpenACC vector. They will host the OpenMP team. And then on top of that, it will be slice, tile, or the whole GPU. Those hardware concepts have no difference, but just they have a common definition as a group of subslice, which you will launch and then you call a group of subslice, you call it a device, and then you launch your OpenMP target region. You launch your OpenACC gang, you launch your CUDA kernel, you launch your SQL kernel to that device. So when we when we want to express our parallelism on the target device, we want to use the OpenMP target construct to transfer the control flow to the device. And here is the simple example. So after you transfer the control flow to the device by the OMP target, you can use the OMP parallel for to further work share, divide your work among different threads. But pay attention here is among different threads. So in this case, there's only one subslice on the GPU is actively working for your loop. So this is our initial approach. It's problematic. It wastes too many of your other resources on the GPU. So we need more construct to use multiple subslices on the GPU. So that is the teams construct. So the teams is another construct. So it's easy to see on the figures. So you have the target construct to transfer the control flow to the device. But then on the device, you're only running on one thread, one master thread. And then you only use one subslice on your device. So in order to use multiple subslices, you use the teams construct. The teams construct will launch one master thread on each subslice in your device. And then each yes, that is the key concept. It's one team on one subslice. If you only have target without the teams, at that time, you only have one thread, you can say one team, but that's just one. And if you do parallel for, under that case, the only one team use one subslice. If you want to use, in the reality, we want to use multiple subslice, multiple teams. In that case, we need OMP teams to launch multiple master threads, one master thread on each subslice. And then once you have that, you can have the OMP parallel to work share within each subslice, within each teams. You can call multiple threads work on your loop. So this is the syntax. You can read it from the slides. And on the clause level, it also gives you the num teams thread limits to control how many teams and how many threads in totally in. So and then we need another we have another construct called distribute. The teams construct is more a hardware concept. It's the compiler kind of put in the hardware information to your executable. It has nothing to do with your source code. It has nothing to do with your application. So basically, it depends on how many subslices in your device. The teams will launch that many teams for you. A distribute is a hardware-software combined concept. Now, if you bring in the information of how many teams you have, also how many work you have in your source code. This is the combination concept of hardware and software. And in this case, it will distribute how many iterations in your loops across different teams. So basically, if you remember the previous page, so for here, the parallel give you the teams give you the threads in each teams, but you still have no, because this is pure hardware concept. You know how many threads, how many hardware threads working in your teams, but you don't know how many iteration actually each thread is handling, right? Because you don't have your source code yet. The compiler have not consider your source code yet. So that is where the distribute come into work. The distribute now will bring in the information from the source code, how many iterations actually you have, and distribute those iterations among the teams and threads you already set up. So now, after the distribute, now you know there will be 32 iterations get into from your source code, get into your hardware team. And 32 iteration will distribute as A to each thread, to each hardware thread. So for the distribute, you finish the hardware software combination to set up the execution policy. So this is called execution policy. It's how you divide your work, how many hardware, how many thread you use, how many iteration on each thread. This is called execution policy. So this is the whole example. We use SAP here. We artificially separate these 4 different layers. So the first layer is OMP target. This one will transfer the control flow to the device. And we also implement that the second data management approach we discussed. It's like we put the map next to the target, which means we use the target to transfer the control flow to the device. At the meanwhile, we also map the data. We also transfer the data to the device. The second part is, so now you transfer to the control flow to the device, but you have not used all the subslice yet. You only sit on one subslice. The second layer is OMP teams. In this case, the teams will make sure the compiler, once the compiler see your teams construct, the compiler will know that it will get the information of your hardware. What is your device definition? Either it is a slice, a tile, a whole GPU. If you get your hardware information and know how many teams you can launch, and launch that many teams. And then each team, inside each team, you have one master thread. So the next one is the third layer will be the distribute. After your compiler get the hardware information, know how many teams you have, because how many subslice you have, all the master thread in each team set up. Now it's the distribute layer. It's the third layer. It's the hardware and software combination. In here, besides the hardware information, the compiler also pull in your source code information, know how your lower bound, upper bound of your iteration, do the math, distribute the iteration across different teams. So each teams know exactly how many iterations they need to handle within each team. And then the final layer, the fourth layer, is the parallel fault and SIMD. In this case, each teams already launched all the threads and know how iterations iterations need to be handled within these teams. And the parallel fault will kind of instruct the iterations run across different threads. And also at this moment, use the SIMD format, which means try to SIMD as much as possible. For the SIMD, in other algorithms, there may not be SIMD, there may be reduction, which means there's a variable that need to catch all the results from all the threads. So this is basically how we express the parallelism. This is the most detailed explanation of the multi-level step P. And then obviously, if you don't care all these details, you can combine them all together with put everything in one line. This is the combine construct. In this case, it will look much like very similar to OpenACC. If you want the descriptive nature of the OpenACC, you can just do the same thing like this in OpenMP. So I still have a lot more to cover I prepare for this section, but due to the time limit, I will stop here as the end of part 1, and I transfer the presentation to Junyi for a case study.
So here, yeah, so I want to report the OpenMP overloading of Gen Intel GPUs. So so Gen team we got a large support from other institutions and also companies. So especially from Intel the company, the Shiquan and Tobias and Harold, and also someone Stephen from the PPL and Dawson from BNL. Nice. So the Gen code is particle in cell simulation code with 40 kinetic electrodes written by Fortran since 1990s. So it aims to study the transport in the magnetic combined fusion devices such as ITER. So it's open source, so you can find our code description and also the code in the website. So it has been ported in different GPUs based on OpenCC and OpenMP directives. So for the NVIDIA GPUs, we ported on Permata from NUSC and Summit from the Oak Ridge. So it used both OpenMP and OpenCC overloading. And also for AMD GPUs, we ported the Gen code on Frontier in Oak Ridge using OpenCC overloading. And for Intel, so we report here, we use OpenMP overloading. So it has been ported for in some spots on Oak Ridge from Oregon National Lab, ANL. So we have some publications about our directive-based implementation work. So it's on peer-reviewed papers. So it has been a special issue paper for ECP and also the conference paper of the 2021 workshop at SC21. So here's a Gen workflow. So first we start from the CPU side. So we will load particles and equilibrium in the CPU side, and then update this data particle array and equilibrium into the GPUs. Then we come to the time stepping part. So our time step part happens in GPUs. So first the particle push. So we will evaluate the particle information or just particle array based on the fields, some potential or electric field, and then we will do some particle shift. The particle shift is that we will sort the particles in different domains. So then the next step is the particle charge. So in these domains, we can, since the particles has been sorted, so we can calculate the density array and the current array, and based on the density and the current, we can do the field solver. And then with the updated field arrays, we can do the particle push again. So this is the whole process of the time stepping project. And then, so here is the OpenMP overloading strategies for Gen on Intel GPUs. So first of all, we need to keep the data on GPUs. So there are some dominated arrays and particles, equilibrium and density and current and potential and some other field arrays. So they're very large. So we want to keep the data on the GPU. Then we don't need to have to exchange data between CPU and GPUs. And then we will apply OpenMP overloading for loops and function calls. So there are two parts. So dominant loops is particle push, particle shift, and particle charge. And also we have the field solver. So it's called of dominant function calls. So we'll do the function field solver, and here we use the dense matrix solver for boson and Ampere solver. So this will also apply, will port it into OpenMP overloading, port it into Intel GPUs by OpenMP overloading. So first, I can introduce the data part. So we have the particle array. You can see the particles are located on CPU side. You can see here, and then we will allocate the data on the GPUs with the same size. Then initialize arrays and the update into the GPU just only once. So just once, and it will, and then we do similar things on the equivalent arrays. Yeah. And we'll come to the different loops. So the particle push, so it doesn't have reduction operation. So we just apply this distribution. It's a very large, actually very large, but we just use the distribution, like what Shiquan was mentioned, as a target things, distribute parallel do, and also some private data management. And for the particle charge, so we have because we didn't calculate the dense or current on the grades, so we use some. We do need some array reduction. So you can see the difference here. So we add the automatic update for the reduction operation. That's the difference. And also we count the function calls. So luckily, Intel supports the native Fortran implementation. So we don't need to call external of libraries, something like foo+ and he+. So here is the example here. So we want to, this is we just give a simple representation of this field solver. So AX equal to B. So we need to calculate is the dense matrix. So we need to calculate the reverse of A. So here, so we just use Omni dispatch, OpenMP dispatch. So it's easily. So the difference between the CPU version and the GPU version, we just add this one. And also for the X calculation, we just use call OpenMP dispatch. So that gives us a very good, very large benefit. So we don't need to change the code a lot. I just use the OpenMP directives, and then it handles everything for me. And then we come to some data. To give you some feeling about the CPU, how fast the Intel GPU it is. So we start from the CPU, CPU versus GPU with single node. So it's test on the Intel internal machines, I think. Yeah. So it's so the test node has one Intel CPU. So it has 64 cores and 128 threads, and 4 Intel PVC GPUs. So on one PVC GPUs, Intel PVC GPUs contain 2 die. So yeah, actually it's dies. Yeah. And so we use 1 MPI for 1 dice. So for Intel PVC GPU means 8 MPIs for me for this problem. So the test problem size we will do the scaling of the particle number, and also we'll some part of the code we don't need to use OpenMP GPU overloading. We just use some multi-threading. So we still, and the multi-threading is 32, and it's a very small problem size. You can see here. This is a great size picture here. So NPI number is 8. So here's the data. So we come to the different subroutines. So you can see P push, C push, P and C is the particle push. So maybe particle evaluation. So we can see we have about 20 average is up to 48. And this grade 1 is the reduction operation. We have 26 and SETW, and this one and others are relevant to reduction. So the most, I think the number is the most, the best part is the PPI. So we have 327 times that. So it's very good for, yes, very good, yeah. Yeah. Then we do the scaling. So we focus on the PPI and the grade 1. So you can see once we increase the particle numbers, the speed up between comparing CPU and GPU will be larger for the grade 1 PPI. So that means that if we feed more data to the kernels, it will be more efficient for the GPUs. Yeah. Then we do the one node comparison between Intel and NVIDIA. So the NVIDIA machine will come from the Sunspot on NL, Oregon, and the Permata on NUSC. So the Intel machine, for the Intel machine, we use OpenMP GPU loading. So it has, each node consists of two Intel Xeon CPU and 6 Intel PVC GPU. So the simulation setup will, because each PVC has 2 ties, so 1 MPI per die and 2 MPI per GPU. So that will be 12 MPI for one node. So, and it means that total composition is physical parameter will be 12, namely km is equal to 12. The particle number per MPI or per domain will be around 64,000. For the NVIDIA machine, we use OpenCC GPU loading. So it's this comes from the machine, a Permata machine on NUSC. So each node consists of 1 AMD CPU and 4 NVIDIA 100 GPUs. So simulation setup is that we use 2 MPI per GPUs. So it's if I want to compare, GPU or 1 GPU versus from 1 GPU from Intel and 1 GPU from NVIDIA. So we use 2 MPI also for the GPUs, for the NVIDIA GPUs. But we use the MPS, it's a multiple process service to enable to make sure to let the GPU, the NVIDIA GPU can have 2 MPIs. And then will be totally 8 MPI per node. The total continuous 8, and the particle number per MPI domain is around 64,000. And here's the data. So, the blue part is the Sunspot, as means Intel, and the purple, the orange one is Permata, as from NVIDIA A100. So you can see some kernel, some subroutines or some kernels, Intel is faster, and some others, NVIDIA is faster. But the overall data is that Intel is slightly larger than the NVIDIA ones. I want to say this is not exactly apple to apple because there's a different system, and also there are different systems and also different CPU side, and also I think the NPI communication is also technique is also different. But I want to say but based on this current data, we want to say that based on the current application, also for the current parameter setting, the Intel GPUs and the NVIDIA GPUs are comparable. Yeah. So here is the summary of the application on Intel GPUs. So we put Gen into the Intel GPUs with OpenMP GPU overloading. And so our strategy is that data is always kept on GPUs. And also the speed up for the kernel is very promising, so up to 300. And also timing with one node on Sunspot and per month are comparable. I mean, Intel's PVC and NVIDIA 800 in this situation is comparable. So we do have some ongoing work for the Gen application. So we're currently doing some large node scaling in Aurora and per month. Then we already have some promising data, but it's not finished. But I want to say they are comparable right now. Yeah. So that's my all I need to present. Yeah. Okay.
So any question for Junyi's presentation? Yeah, go ahead.
So the speed up 300 times, was that per core or for the whole node?
As a whole.
The whole node?
Yeah,
Sure.
yeah, whole node, yeah, whole node. Because I think there's some reduction operation there, and the reduction operation can dramatically benefit from the GPU. I mean, reduction. I mean,
Mhm. And so that was 4 Pontivecchios versus the whole node, or 1,
yes, CPU,
or,
yeah,
or
yeah.
8 tiles.
8 tiles, yeah, yes, that's
Okay.
true, yeah.
Thanks.
It's not the question from this presentation, but the before we went for a break. So what is the difference between open FI OpenMP and F OpenMP?
So basically, at this moment, you can just treat them the same. So previously, there's one with a little bit Intel implementation dependent implementation there. But now I think the difference between those two are very minimum. Usually, you will not notice that.
Is there any advice on which one to use, or like which one is the recommended one to specify?
Q OpenMP.
Okay. And so yeah, so the device side in partial GPU's allocation, how does it like? So if I have multiple subslices and each subslice is treated as one GPU, so how do you infer the device ID in that case? So you said you can partially allocate the GPUs, right?
Yes.
And those partial allocations are basically the subslices or different?
So you partition your whole GPU into different device. So each subset of the physical GPU now become a one device be viewed for the source code. So the source code, in that case, like each MPI rank, it will only see one device, which is one partial set of your hardware. Because that's one device, so in your OpenMP source code, the device number will always be 0. You don't usually you don't specify device number within the source code using that device construct. That part happen outside the source code on your MPI host device binding procedure.
And what is the command to specify the partial GPU?
That's that usually you need to go to ask the admin on the supercomputer. It's
It's not
basically
which user can create his own, like user cannot partially allocate a GPU.
yes, you can. There is a set of slum or PBS command. It's a set of slum or PBS environment variable.
Okay.
Yeah.
Thank you.
So you don't need to worry about that in your source code. And when you reach that step, when you need to partition the GPU, at that time, probably you go to read the manual of the supercomputer centers. I'm sure they will have a chapter talking about MPI, talking about the host device binding under the MPI scheme. Because the three things are tied together: the scheduler, the MPI implementation, the host device binding approach. These three are all together. You need to have the information from all three before you can successfully finish the process. So you don't handle that in your source code.
Thank you.
All right, any other questions? Maybe I'll ask a quick question on the the porting work and the comparison between the OpenACC and OpenMP. Maybe, sorry if I missed this, but was the code ported to OpenMP and OpenACC in separate efforts, or was it ported to one of those? You know, was OpenACC added first and then it was converted to OpenMP, or vice versa? And then maybe can you speak to the level of effort first to port it to the GPU and then to switch between OpenACC and OpenMP?
Okay, yeah, we had was a conference paper at SC, so saying that what was the effort from OpenCC to OpenMP. So they will start. We definitely start from OpenCC firstly, and from NVIDIA machines, and then actually at that time was in 2021. I think OpenMP offloading is just coming out. So we did a lot of work effort on that, and also found a lot of bugs at that moment. But I ran eventually, and these bugs are gone. And also we work with Shiquan, and then we just give the OpenCC code to Shiquan, and then they have there was a tool, it's the ACT to OpenMP, and we use that tool, and it's just maybe several weeks it's done. And but there's still some bug and also some performance, so it's not so good. So we do some statistical work on some loops and to improve the performance. And then I think I don't know if you will mention that loop or not, but just one loop. It's too slow, and we just spend some time on that. And that's all we did that. And also spend, I think, maybe just 1 month as enough for that specific loops. Yeah. But I honestly say if back to the 2021, maybe it's not this story. Yeah, you need to spend a lot of time on that. Yeah, but currently it's much better than before.
All right, thank you. All right, Shiquan, why don't you continue?
Sure. So now we will continue to the part 2 of the tutorial. Let me share my screen. So thank you everyone for coming to my tutorial today. This is the part 2 of our tutorial of OpenMP offload to GPU and Intel Fortran compiler IFX. So for the second part, basically we already heard the story of a successful application implementation of OpenMP on a plasma physics simulation called GEM, presented by Junyi. Now, actually, here is another semi-application example. We will show you how to how the OpenMP offload MKL a function call solving a linear system on GPU. So this is something the introduction similar to the part one. I will not spend too much time to explain the one API, how one API solve the heterogeneous programming challenge. I will just flip the slides. So this is talk about the device model. Again, for the currently we are use this host device model, one host driving multiple device of the same kind. And this is the memory model we explained before. And this is the high level. This is the high level architecture of. I keep flipping. So basically, wrong. I have some technical issue. Let me stop. Yeah, I need to stay in this mode. So this is the high-level architecture of the OpenMP offload to GPU. So we start with the the base language source code file with OpenMP directives, and these can if it is CPU, we go through the OpenMP CPU runtime. If we have the OpenMP offload construct, we go through the OMP offload runtime library, libOMP target. And the libOMP target have two different backend. One is OCL, OpenCL plugin. If eventually we want to offload back to CPU, we go through the OMP's OpenCL plugin. Or if we use offload to GPU, we have two paths. We can go through the OpenCL plugin and then the GPU OpenCL runtime, and then generate the GPU kernel mode driver, call the GPU kernel mode driver to generate the GPU code. Or we can go through the level 0 plugin and go through the level 0 runtime and call the GPU kernel mode driver to generate the device code. So this is the compiler support we see before. Basically, we use the -q OpenMP to enable the OpenMP. Then we use the -f OpenMP -targets equal to SPIR64 to specify the backend for the device offload. So the OpenMP offload program mainly include two parts: the data management and the kernel execution. So to manage the device data, we mainly use the map clause after any construct, whatever construct you need. It can be OMP target construct, which will transfer the control flow. It can be OMP target data construct, which will only transfer the data. So for the map, the syntax is below. So the general syntax start with OMP target and then map. And then it's optional. You can specify the map type modifier. And then you separate by comma. Then you specify your map type. And then you put a column there. And then it is a list of variable. For the map type, it can be to from, and also a log. And then we also release and delete. Usually release and delete is not that common to use. And so that will define the map type. And there's more subtle behavior, which is called map type modifier. It can be always. In that case, the variable in the list will always be copied. That will enforce the data movement. Another most important map type modifier is the present. It will order basically it will check the data if it is on the device. If it's not on the device, the code will crash. This will keep so basically for the present, it will make sure there's no data movement actually. So go ahead. Hi.
I was just going to say, maybe, I don't know if we can try maximizing the slide again. I know it was advancing on you before, but that one's pretty hard to read, at least for me.
Oh, okay.
In that mode. Thanks.
So basically, the present will make sure it does not copy the data. So the present map type modifier is important. It's because lots of directive programming approach right now implementation is based on OpenACC. For the OpenACC, the present there's a present clause. The present is very high level in the on the programming model. For the OpenACC, the present is right next to the construct. If you give the ACC parallel, and then you can as the construct, which transfer the control flow to the device, you can immediately say present, put the present as a clause of your ACC parallel. So in that case, if you the compiler know that the programmer only want to check if the data is there. If the data is not on the device, just error out. So that kind of like keep a much faster cycle for the debug and for the to keep the code simple. But for OpenMP, this is kind of like the disadvantage in the implementation, because the present behavior barrier so deep under the programming syntax structure. In order to perform the present behavior, which means in order to perform the check, the data checking, just check to make sure the data is on the GPU, we need to go through the clause level, which we need to assign the map. We want to pretend we want to map the data, and then we need to provide a map type, which actually if we only want to check the data, the only viable combination is set the map type as a log, which doesn't make sense. And then after we set the map type, we set the map type modifier as present. So we need the whole thing. We need a map, present, a log, 3 layer, the clause, the map type modifier, combined together to implement the behavior of present, which means checking the data if the data is on GPU. if it is not error out. So this is one of the important difference between OpenACC and OpenMP. OpenACC actually get the advantage here by have a much simpler present behavior implementation, which means the data tracking implementation. So here basically this is a review of the section, the part one. It's like we mainly talk about we can use two types of data environment, the structured data or the unstructured data. The structured data, which means you only stay at one compilation unit, one source code file. In that case, you know what you want to copy back to the device when before you copy to the device, before you at the entry of your data region. And you also, when you copy back the data, you exactly know where you get the data from. You know your entry of the target data region. And also for the unstructured data, in that case, the OMP target enter data map can exist in function subroutine A, and then you can have a target OMP target region and subroutine B, and then you can have a OMP target exit data at subroutine C, and those can be very flexible, and they don't need to come into the same library or stuff. You can have a different developer, different programmer writing different subroutine. They are not in the same source file. So kind of like these two are the most useful data management scheme. And there are two types of computational kernel. One is the loop structure. Here is some simple example. The loop structure can be nested and can have reduction operation. And usually we don't want to put the if structure, we don't want to put the control structure inside the loop. And obviously it cannot have certain dependency. The backward dependency is not okay. The forward is okay. So for the function call, if we want to put the function call on the GPU, that process is called dispatch. So conditionally, we will try to call that function with a version of device code. If that we call it a variant, we will try to call a device variant of that function if it is available. If it is not available, then it will fall back to run on the host. Usually the main difficult part comes from the data management part. We need to make sure that the code handle the data mapping properly. The MKL provides an explicit API, MKL_matlock, to do the data mapping. But usually we try to do it in the source code level. So after we understand that the dispatch process itself, actually it is pretty simple. It is just say OMP dispatch. And Intel currently provide an Intel only implementation, which is called target variant dispatch. I think in the future we will remove this. We will only use the open specification of which is OMP dispatch. So usually for Fortran, we can stay. We are good to stay with the OMP dispatch, and the OMP dispatch is a construct. And under this construct, there are multiple clauses we can use. It can be depend. You can use device, and then you can use interop. The interop currently it's under construction. That is the main feature of OpenMP 6.0. It will come out by the end of this year, and then we can use its device pointer, and and no context, no variant. And also we can do the async offloading by putting the no way clause. In that case, the control flow on the host will continue without waiting the device control flow come back. For the C and C++, we can also use the OMP target variant dispatch. This one is Intel implementation specific. It will not work on other vendors' OpenMP implementation. They carry out a pretty similar available clause between C and Fortran. So next, let's briefly talk about the OneAPI math library, which is OneMKL. So basically, it provides a BLAS, a sparse BLAS and LAPACK, FFT, and also it vectorize the math function and provides random number generators. So we can use both the target variant dispatch or the dispatch directive. So here is some support page for OneMKL. The most useful thing is the Intel the MKL link line advisor. So basically, you fill out the menu, you check the menu as is shown on the screen. And then after you input all the information on the right-hand side, you will get those link line result on the left-hand side. You can copy and paste into your make file. So here is some documentation for the optimization guide. So here is an example solving the linear system. This is we have a published paper on this and the source code on GitHub. So basically, we want to inverse a complex double matrix. For here, basically, we use the unstructured data approach. We use the target enter data construct, and then we use the map clause to settle all the variable on the device. Because this is a simplified example, I only have one source code file. So you can see the OMP target enter data is in the same file. But there's no problem that if in your view application, you can put this in, you can put the OMP target enter data at your initial module, at another source file, at another module, at another compilation unit. That's totally fine. So this will still work. But it's your responsibility, it's the programmer's responsibility to make sure you map the data properly. And the same thing applies to the OMP target exit data. You don't need to put it at the same source code file. You can, if your code is complicated, you have a finalized module, you have a finalized subroutine. It's perfectly okay. You put the OMP target exit data there. Or the other way, if this is like a time step iteration, like we made that at the jam, you can put that exit data at another subroutine, which when you need to collect the data from the device. So, but for our simple case, everything is in the same source code file. So after we settle how we transfer the data, the actual dispatch procedure is super simple. It is just for each function call, we do the dispatch. And pay attention here, because for solving a matrix or inverse a matrix, it have two steps. First, you need to do the factorization, and then you either do the solution or you do the inverse. So that will be two separate function call. In this case, because they live in the same data environment, so you can see there's no data movement, there's no data mapping between two function call. We just do the dispatch, will be fine. So also, the one MKL also provide another type of data structure which is called batch matrix, which is you flatten each two-dimension matrix into one dimension, and then you put multiple matrix into one batch matrix. So there's the same set of function call for batch matrix. And if the matrix, all the matrices have the same size, that is strided, you use the strided version. If each matrix has different size, you use the unstrided format. And usually you need to test several times to find the best workspace size for your application. And so basically, this is the compiling command and the one-time command. So basically, we get this information from the previous slides, especially the what MKL link line advisor. So also to compile the OpenMP offload code, we can do just-in-time compilation and ahead-of-time compilation. By default, it's just-in-time compilation, which means the device code, the compile and the linking process will not generate the binary for the device code. It will only generate the IR, intermediate representation, for the device code. And it's during the runtime, the one-time compiler generate the kernel code. This is not by default compared to other vendor. So other vendor, the NVIDIA, AMD, they always do ahead of time, which means during the compilation and the linking, they also generate the device kernel code. So in order to do the ahead of time AOT compilation, we need to change the flag a little bit. Now it's not SPIR 64 anymore, it's a SPIR 64 underscore gem. And then we also need to provide the backend. The backend is which we need to provide the PVC, our GPU version. So here's about the data movement. So basically, the most important thing is that usually we don't want to solve small matrix on the device. They won't help us. We usually put the large matrix on the device. So when we handle the large matrix, we usually only need to make sure that large matrix don't get copied back and forth if it is not necessary. The other small value, small scalars, they will not affect the performance that much. For our case, the large matrix is about 4 gig. So we want to make sure it only moves from the host to target once. So, and we have an environment variable, which is called the OMP target debug. And for that environment variable, if you print out extra debug information from the runtime, and then you just save the screen output and grab the keyword moving. And then basically you can recognize that large matrix size in your source code, and you want to make sure that large matrix does not get transferred unnecessarily. So here are some useful environment variable for the OpenMP, including the OMP target offload, which we introduced before. We can set it mandatory to make sure it run on GPU, or we can set it disabled to make sure it run on CPU. And then we also can choose the backend, either OpenCL or level 0 by the OMP target underscore plugin. And then we can choose the debug level from 0 to 2. And then we can turn on the profiling information by true or false. So for the 16,000 by 16,000 matrix size compared to the CPU and GPU, the speed up is significant, close to 10 times. So here is some other thoughts. So for example, we should avoid this full matrix assignment operation. It looks very simple. It's just a very short line in your source code, but actually this is a very expensive operation, especially on device memory. It is not mandatory to use the allocatable matrix in the Fortran case, but if you make it more robust, but sometimes a little bit slower, and use a realistic matrix to test the performance, because sometimes we for simplification, we set a lot of zero inside the matrix in our test code, but the MKL and the compiler, they are smart enough. If they see a lot of zero, they will shortcut. They will kind of skip a lot of computation. So make your codes run artificially super fast. But in the actual problem, when you don't have those zeros, your code runs slow again. So, and then also for the MKL dispatch, we need a dash IA to set the integer as a integer A type that's needed to make sure the code of dispatch correctly to the GPU. So we have profiling tools called unit trace. In that case, you can wrap your application with the unit trace and then get the trace file and copy back to your local machine and just use your Chrome browser. You can see the trace result. And also you can hook up to our vTune by some simple command like this, and then the vTune can give you some report about how well your code runs and what is the bottleneck. So I will take another 10 minutes to talk about OpenACC to OpenMP migration tool. So, sure.
Okay, so you said you have to use -I8
Yes.
to use the MKL offload.
Yes.
Doesn't that conflict with MPI? If you do -I8, well, maybe it breaks only the older MPIs, but then 8-byte integers cause a problem.
Yeah, there will be problems.
Yeah.
You need to make a pretty complicated compiler flag setup to kind of isolate those. Because probably you don't need the offload, the MKL offload at all the source code file. Probably you need to figure out a way to make them live together.
So I guess you could have a separate file with just -I8 for the offload.
Yeah.
And no MPI in there.
Yeah, unfortunately, at this moment, the MKL offload. Yeah.
Okay, let's verify.
Yeah, we meet that situation. Yeah, unfortunately at this moment the workaround is you put them in separate files and you use a different compiler flag. You put a switch there to handle. Depends on which one is the priority. So this is pretty new, so sorry about it's very wordy. I don't have any good figures to demonstrate the tools. So it's an open source tools. It's available on GitHub, and we have a conference paper talk about the code. And so basically the takeaway from here is we only do symmetrical translation. We don't touch we are not deep in the execution level, binary level. We are not in the executable level. We only, basically, you can think of this as a text parser. We only convert line to line between OpenACC to OpenMP. And another take-home message is we only guarantee the correctness of the translation, and we have basically the performance is not in the scope of this tool. You still need to optimize your code after the migration. So basically, this is how you evolve the tools. So basically, you find the path to the translator, and then the executable is Intel application migration tool for OpenACC to OpenMP. It's a very long name. And then the SRC can be a file or can be a folder. And then one popular flag we need to use is async equal to none. That will ignore the asynchronous OpenACC statement. Because OpenACC and the OpenMP at this moment, we do the sync and wait in a different way. So it causes you more trouble if you translate that part by the tools. It's better you examine how the code sync and wait in your original code and put the correct implementation of OpenMP in the new code. And also some of the API is not translated because they have a different way to do the they have different API calls. So here are some highlights in our current experience, kind of treat it as a BKM, best known method. So the set device, the ACC set device num will be translate. The most similar OpenMP API will be OMP set default device, and combined with the environment variable OMP default device. So this is the best you can get close to the set device num in OpenACC. And the ACC data create will be most similar to the OMP target enter data. And the most time-consuming loop, the most time-consuming region in OpenACC usually is it's ACC parallel loop. That course will be translated to OMP target teams loop. We need to specify the team. Basically, the target teams loop is already a combined construct. It's the combined construct of target, construct teams, and the construct loop. So if you compare side by side with the ACC, the ACC just two construct is the parallel and the loop. You can imagine the loop is the open ACC loop is corresponding to the OpenMP loop. And in that case, the ACC parallel actually it corresponds to two construct in OpenMP, which is the target and the teams. Because in the OpenMP, we need the teams to launch multiple master thread across different subslices. Otherwise, the OpenMP will only use one subslice, as we explained in part 1. And the next one is the present. For the present, I explained before, the OpenACC implementation will be really simple. The present is in the clause level, but unfortunately for the OpenMP, the present is deep inside the map type modifier. So you need a special combination of map present a lot to mimic the OpenACC present behavior. And finally, the ACC atomic update will have it's an important construct. We have a counterpart OMP atomic update. We can use that. But to handle the atomic operation, the OpenMP actually have a lot of support of reduction. Sometimes you can use reduction instead of atomic. Okay, so this is all my presentation today. Thank you. Oh, any question?
Maybe I'll ask a question to start things off. So you had mentioned that the two different, there was like the OpenCL backend and then the level 0. It looked like, I guess, if you wanted to produce CPU code, it looked like you would have to go through the OpenCL backend. Did I see that right?
Yes.
Is there any other reason why you would choose one or the other, or is that pretty much the only distinguisher?
You don't need to choose. I'm not sure I understand the question correctly. So if you don't specify anything, the compiler will make the right choice for you.
Yeah, well, there was one slide where you showed some environment variables, and there was one environment variable where you could select the backend. And I'm wondering if there's ever a reason why the end user would want to do that.
Oh, yes, I got you. Usually you don't need to. That's just an existing knob there. If there was some special reason the users want to control that part. I don't have a user case why the user want to control that part, but the knob is there.
Okay, so yeah, it's kind of just for awareness, but probably not going to use it.
Yeah, you don't control that part unless you know what you want to do.
Any other questions in the room?
Now, since you work both with OpenMP and OpenACC, I mean, we worked recently with OpenACC to port the Muram code to NVIDIA GPUs. And one of the most painful things I experience on a daily basis is that with the NVIDIA compiler, I get very often these partially present errors, which have to do some way with the GPU memory management. I just wanted to ask the two of you if you have seen something similar and if OpenMP is much more robust in that sense.
Usually that pain point comes from they change the default behavior silently between different versions. That sometimes breaks your code. The OpenMP is not 100% free from that issue. We also see a similar issue. And but for the OpenMP approach, if you write the code in the implement the OpenMP, the OpenMP code still can run on NVIDIA hardware. So and for the OpenMP, for the specification, it provides you more knobs, more explicit control. So probably it will help you to build your code more robust if you also implement the OpenMP approach. But they can live side by side with your OpenACC approach. Mm-hmm. And you can compile the OpenMP approach with NVIDIA compiler. But currently there's an issue. There's a roadmap decision that for currently if you compile your OpenACC implementation with Intel compiler, it only runs on the Intel previous GPU. If you want to run your OpenMP implementation on NVIDIA hardware, you need to use the NVIDIA compiler. Okay. Yeah, but from the specification level, it helps. It makes the implementation more robust because you have more those syntax, those data mapping are more strict on OpenMP. Yeah.
I don't, yeah, for my experience, I think we start from OpenCC always because, yeah, that I want to say if you put the code into OpenCC, and OpenCC does have the CPU virtual architecture actually. So I tried OpenCC for CPU, it's very slow. But if you put the code onto OpenMP GPU offloading, just you can use the compare option to just run the code on CPU side. It works and it's much faster than OpenCC CPU version. So that's one benefit I think. And yeah, another thing is we're talking about the present data, the data management. Actually, the present is always used for actually for debugging. Just yeah, if you can remove that eventually, present I mean the data, yeah, because it's already there. We just check, and that won't give us any. Yeah, that's the difference. And also I think OpenCC is so you can use OpenCC for NVIDIA machine and also can use for the AMD machine. But I don't think it can be used for Intel machine right now. So it says OpenMP of Chmielowiec can be used for three, I mean, NVIDIA, AMD, and Intel machine. So that's one benefit. Yeah. Another one, yes.
All right, well, if there are no other questions, I guess, Shiquan, are you two going to stick around through the lunch or do you need to head out?
Yeah, I stick around.
Okay, so yeah, if anybody has questions, further questions that come up like during the lunch hour, feel free to track them down. I think lunch won't actually start until 12:30, but we'll obviously break for an additional 10 minutes. And then there's a second tutorial on UXarray, and that will start at 1:30. So hope you all enjoy the lunch and see you back in here for the afternoon. And we can thank the tutorial presenters again.
Hello, in-person attendees. I'm just letting you know that lunch is ready. Please take 2 halves of a sandwich, not just one, and maybe even 3 if you're feeling hungry. So thank you.
great, yeah.
All right, so it is 1:30, which means we're gonna get started again with the second tutorial of the day. And this will be a tutorial from Orhan and Philip on UXarray. Any other announcements you'd like me to make? Otherwise,
I think we can get
great.
started.
Yeah, and I think if anybody has questions, I'm happy to pass a mic around in the room, and we'll use Zoom chat for online participants. So yeah, just raise your hand and I'll bring the mic to you, and that way the people online can hear. Thanks.
Yeah, sounds great. Thanks so much. Thank you for the introduction. For this, is audio level good? Okay, great. Thank you so much. And can I share my screen? Let me do that. Okay, not this one for sure. Okay. I think we can start with this one. Again, hello everyone. Please let me know if at any time audio level gets worse or maybe things arise. Just let us know, and we can try to make things better. My name is Orhan Eroglu. I work at NSF Ankara, CISL, and I do work with Philip on this UXarray project. Philip, would you like to say hi to our audience?
Hey everyone, I work with NCAR, or I work with Orhan at NCAR on the GeoCat team, and I'll be virtual for this presentation. So I'll be keeping track of virtual questions in the Zoom chat as well for anyone that is also attending online.
Yeah, thank you so much, Philip. And I'd like to acknowledge one thing. Philip did make a UXarray presentation today at 2-ish a.m. to EGU. So, Philip, thank you so much for still being with me. And I hope that one went well for you as well.
It did go well. Thank you.
Today, we will do a UXarray visualization tutorial. I'd like to say, so far, the opportunities we had to demonstrate this thing to people were most of the time end user focused. Today is going to be different. We have a lot of like software engineers here, and I'd like to add a flavor of software engineering things as much as we can. So to help with that one, I'd like to have everyone feel the confidence to interrupt anything at any time. We have plenty of time, more than enough, I think. So if you have anything, a question or anything else you would like to contribute to the discussion, please go ahead and interrupt, and we can answer the questions at that point. Let's get started. So as we mentioned a number of things here, I will be the in-room presenter today, and Philip will be presenting some of the material and also keeping a pair of eyes on the Zoom chat. If you would like to put your questions into the Zoom chat, so they will be caught up by Philip as well. And again, as I mentioned, feel free to interrupt at any point without thinking if the subject should be cut or not. And that could be through raising your hands in the room or just unmuting yourself in the Zoom and starting your question. That could be anything else. So just feel free to do that. Today's content is going to be delivered with the help of a project called Project Pythia, and in the form of cookbooks. So you can check Project Pythia cookbooks afterwards. There are plenty of them. Project Pythia is purposed on giving people in the geoscience and earth sciences some foundational knowledge and some deep knowledge of different application fields. In this context, we will be using Project Pythia cookbook, one of the cookbooks for UXarray visualization. And in particular, the cookbook we will be using for today's purposes is the UXarray cookbook, as we have linked here. So I think before we jump into the tutorial of today, it would be still helpful for everyone in the room, even if you are a software developer or you are a potential end user or already an existing end user of the UXarray. This motivational slides for what is UXarray, what target end users we are trying to put UXarray for, and what functionality we are developing here and how we are doing that kind of introduction would be helpful for everyone. So in UXarray, hopefully the name is suggesting, but if not, it is unstructured Xarray. So if you are familiar with Xarray to some extent, like if you are using Xarray for structured grid analysis or visualization, you can assume UXarray is building upon Xarray functionalities and data structures and putting a capability to recognize unstructured grids, unstructured meshes, to introduce data analysis and visualization functions. And on the left-hand side, you can see a regular lat-long grid, and on the right-hand side, you can see two examples of unstructured grids. And the main motivation behind us developing UXarray is there is a slow but steady transition from structured grids to unstructured grids because of the much finer resolutions, like kilometer scale resolutions coming in place, and the size of data getting large and large, and the climate analysis and visualization is going to be making more use of unstructured grids in the coming future. And there are also some other motivating factors here. For example, despite the transition to unstructured grids, there has not been any widely used software tools in the scientific Python ecosystem, which was one of the pioneering factors behind us doing this UXarray development. And there are just a few analysis tools, even if they are not in Python ecosystem, and most of the time different communities and different groups are using their own solutions for unstructured grid data analysis and visualization purposes. And because of that, there are also a number of different unstructured grid models, and there was not any consensus between or an implemented consensus between the community groups when it comes to unstructured grids. And kilometer scale, which is, we can also call it global storm resolving resolutions. They generate huge sizes of data, and because of this, data analysis and visualization with unstructured grids, especially with larger data, is really challenging. And another challenging factor here in the very bottom of this slide is even if a functionality is just straightforward with structured grids, it can be quite complicated when it comes to applying the same algorithm to unstructured grids because of the nature of unstructured grids. And just a heads up, throughout this tutorial, you will probably be seeing me or Philip using some terms like grid or mesh or maybe some others, just in place of one another. So they are all the same. So unstructured grids or unstructured mesh. And whenever these kind of terminology things arise, I will be doing my best to let you know. So yeah, we talked about it. On the left-hand side, you can see the data analysis and visualization functions we are trying to implement, but at the same time, we are trying to do this in a scalable, open source development manner. And on the right-hand side, we are not only trying to put together a tool and maintain it by ourselves for the entire life of the tool. We would like to lead some sustainability here, which is only doable with some community ownership around this tool. And because of this, we have created an unofficial partnership with another project from DOE, which is called Project Seeds. So the NSF parts of the UXarray is Project Rygene, and we are unofficially partnering with DOE folks through their Project Seeds. And with the help of this unofficial partnership, we were able to create UXarray, and we are also looking for further partnership here. So if there are people, there are groups in the community, they would like to be part of UXarray, we are more than welcoming anyone else. But actually, community creation and community ownership is not stopping at that point. So let me first get you focused on the technicality of the UXarray, then we can also look into what we have done so far to gain some community familiarity and maybe a little bit of ownership, and what we are going to be doing in the future as well. So another point here, on Thursday, Philip is going to be having his own UXarray talk. Some portion of this talk would probably feel repetitive to you, but I will try my best to stop at those points where Philip would be probably clarifying more on Thursday. But just inevitably, because of this tutorial, we need to communicate some of the UXarray background information with you to get the things more clear throughout this session. So as we mentioned, UXarray is building upon Xarray functionalities. This may be a little bit crowded, but let me do my best to give you the biggest takeaways from here. Let me see if I can use this. The pointer poll. Is the pointer working? Maybe it's because I'm sharing my screen. Okay, yeah, anyway, I can use my cursor. One thing here you can notice, I had mentioned one thing about the driving factors about UXarray. So there were communities who were using their own unstructured grid models and data formats and grid formats. And because of that, you can see there are a bunch of different conventions and grid models and things like that communities had a tendency to use their own, like MPass, ChemSE from like in-house NCAR, and there are some ICON from the European folks, and there are some others. ESMF connectivity is also slightly different than script as far as I know. What we did here is with the UXarray to unify them into a UGrid motivated model. So we are supporting all of these, and we are also providing as part of UXarray a plugin like structure to introduce your own grid model into the UXarray tool as well. So UXarray can, in a uniform manner, represent all of these things in a UGrid-like implementation. And one other takeaway here, as you can see, the UXarray data structures are heavily relying upon XArray's native data structures such as dataset and data array. You can see that here, UXarray has a corresponding UX dataset, which is actually inheriting from a software engineering terminology, inheriting from XArray dataset, and the same thing applies to UX data array. What UXarray does here on top of XArray is the recognition of unstructured mesh or grid with the help of this grid object. So we are storing any grid topology related information into this grid object. And besides that one, we are still using data structures for data analysis and visualization purposes for any of these functionalities. Today's tutorial is going to be more on the visualization parts of the things. So because of that, I'd like to communicate about this diagram as well. It is a little bit more crowded, but I'd like to give you a few senses here. So in each data structure, as you can see here, are UXarray grid, UX dataset, or UX data array. We have a corresponding dot plot accessor, just like you would see in the XArray workflows. So if you have a data set to analyze, you have your dot plot accessor. Whatever function there is, you can use them just like you would do in the XArray counterpart. And we will be seeing a lot of examples about this throughout the tutorial. And that same dot plot accessor applies to grid object. If you would like to analyze your grid object, you can run your dot plot functions through the grid object, and the same thing applies to data array too. What are these like color-coded diagrams telling us is we are not only generating some other visualization package compatible data structures such as a geodata frame for spatial pandas or poly collection and line collection for the matplotlib package. We are also wrapping up the functionalities, visualization functions from HoloViz tools of a stack of tools. So our UXarray native visualization functions are wrapping up these functions from here, but at the same time, if the end user of UXarray wants some other functionalities for to use them with their own visualization package of interest, they can still get some of the data structures such as these out of UXarray, so that they can just bring them to their favorite visualization package. So we are kind of doing in between, like we are letting the end user know and use some of the visualization functions and also get some data structures as well. The community creation parts of the things is not straightforward. You as a project development team have to do a lot of things to ensure you are getting some community interest and hopefully gradually some community ownership as well. So we have been doing everything publicly on GitHub, not only the code itself, but also all of our project development lifecycle related things such as project management through the GitHub project boards and other project lifecycle related activities as well. No need to say we have open source our code. We build on Pangeo community and Pangeo software stack, and we are in close collaboration with Pangeo folks through our like weekly meetings and activities, and also some really strong discussions about what to do in the initial stages of UXarray to make it more like Xarray. We have been trying to document very well with the help of a lot of usage examples, API documentation, user guides to make sure our end user is not only understanding better the unstructured grids, but also how to use UXarray tool in close relation with Xarray and their existing workflows. Yeah, major design decisions have always been made throughout GitHub discussions so that we can get the feedback immediately from our community and end users, just like almost another software package today in the scientific Python ecosystem. We have been doing our CI/CD infrastructure on GitHub as well, and lots of examples. When it comes to the community ownership, it's really not easy, but we are doing some activities to trigger community ownership to make it more sustainable for UXarray in the rest of the project lifecycle. So for example, we have done a lot of requirement and specification discussions with the immediate community members throughout our GitHub discussions to make sure not only the requirements, but also the specification and design were made through some community feedback. Implementation itself. So to motivate some community ownership, you have to first give the community and end users some good set of significant functionality. And we have done this for the data analysis and visualization parts, especially for the visualization functions. We have implemented a bunch of usable functions so that we now are able to go ahead and give demonstrations and community feedback activities that is really helpful for us. Also, we are working with the community members if they would like to introduce their grid formats. So I think the most recent example there is the icon. So we will be probably in the near future introducing icon as part of our discussion with the European communities. For documentation, not only usage examples, but also the cookbook we will be going over today, and tutorials, demonstrations. We are trying to put user guides as well to make sure unstructured meshes are being understood properly, and also the UXarray is being communicated to the end users and maybe user contributors in the future as well. This is just a reference slide you can check out afterwards for Project Pythia resources, because not only for UXarray as the topic of today, but you can find a lot of useful information if you would like to, if you are a person who is transitioning into scientific Python ecosystem, or if you have team members, if you would like them to learn more about how to use some of the Python foundational skills for geoscientific data analysis and visualization purposes, I think you can find some useful information about under the Project Pythia umbrella. I am also personally a part of Project Pythia development team. So yeah, I think that will be helpful for you to check out and see if there's anything helpful under the Project Pythia. Let's see what we have. Actually, this is for the rest of the tutorial. I think we are good to wrap up the slides and introduction at this point, and maybe look into the actual cookbook now. This is the cookbook I have been talking about from the beginning of this tutorial. that's called Unstructured Grid Visualization Cookbook. And this is the project PTR portal actually. If at any time you go ahead and click into the cookbooks, you can find bunch of cookbooks here for different application fields and subjects. For the tutorial of today, we will be looking into the Unstructured Grids Visualization Cookbook that was made for UXarray especially. And I think we can get started to why UXarray, what UXarray is aiming to perform, and who is our target audience. One other motivation here is, again, people have different tools to make data analysis and visualization for unstructured meshes, but in many cases, they had to do regridding from unstructured grids to structured, then perform analysis or visualization operations. One, I think, strength I'd like to say is with UXarray is we are putting together the functions to be executed on natively unstructured meshes rather than needing to regrid them into structured meshes. And also the grid information such as connectivity is being used under the UXarray functionality. And because of these, there is a limited need for pre-processing the data prior to the actual data analysis because of this regrading need is taken away. I'd like to first give a quick introduction to what is unstructured grids and what would be the difference from structured grids if you were working more with the structured grids. But before then, I would like to ask if there is any question. Do we have any questions so far? Any questions through Zoom?
There's no questions online.
Okay, sounds great. Okay, if any questions, please let us know. The main difference between structured and unstructured grids, let me first show you two visuals to make that difference really apparent. Then we can look into some theoretical differences as well. So if you are looking into a lot long grid and assume this is the global map, you can see such uniformly distributed lot and long cells or grids, right? So there are some disadvantages with this, with the finer resolution. So if you would like to have a really fine resolution, such as global storm resolving resolutions, like a few kilometers, then even if you are not interested in some parts of the globe, like you are not particularly interested in poles, for example, you have to still have a lot of grid cells because of this distribution. But when it comes to unstructured grids, in this case, this is just a triangle, a set of triangles, but in general, you can have any triangular, quadrilateral, or whatnot geometrical shapes for unstructured grids. But in this case, that's just triangular. And this is a very naively generated unstructured mesh. There is no actual analysis value in this one. And there is no actual UXarray relation to this code. So it is just like generating triangles, as you can see here, just to give you a sense of what an unstructured grid would look like in comparison to structured grid. So as you can see, there are triangles here. And another terminology heads up here, we call each of these shapes as face or cell in the unstructured grid terminology. And these points or nodes, actually, nodes and multiple nodes generating faces in this grid. And what else I can tell? Again, there is no direct relation to UXarray from this code, but the only purpose here is to give you a sense of how an unstructured grid would look like differently than the structured grids. Let me see if I can give you some, yeah, like because of this unstructured creation, you can really adapt your global map into some regions of interest with much finer resolutions, while you are leaving some parts of no interest with really coarse resolution with the help of unstructured grids. And also, if you can do like local refinement, you can also increase your visualization capabilities with the local refinement as well. And because of this local refinement capability, you can efficiently scale your data size. So you don't have to create faces or nodes for the region of globe if you are not interested in, for example, the poles. So because of that, you can just refine the size of your data as well. And because of this, UXarray has some implementation aspects. So UXarray, first, as we mentioned before during the slides, enabled significant set of data sets, data analysis and visualization functions. And because of that, even if you are using a data model or grid format different than other people or other groups, you can still use UXarray, or you can easily introduce your grid format into the UXarray with the help of the code structure. And the team is always motivated to help you out with that one, with that extension capabilities. And as we mentioned, Xarray is the heart of UXarray, and if you are familiar with Xarray code development or workflows, you can really get started easily with the UXarray functions as well. Another thing was the standardization. So that was the big issue within the unstructured grids world. So people had their own models, and even though there was some conventions like UGrid conventions, there was no direct consensus around people need to implement them in the scientific Python ecosystem. I think UXarray is kind of bridging the gap for that need to provide people with a unified data model under the hood. And it is still UGrid compatible. So because of our implementation, we are still implementing the things around the UGrid conventions so that people can still see UGrid capabilities. And because of the Xarray compatibility, I think it would be fair to say we are building on optimized data structures, which would be also scalable with the help of technologies like Dask and so. I think we have covered this already. Next, even though the next topic is data structures, I'd like to give this one first because it has some geometrical representation of how an unstructured grid looks like. So this is a very simple geometry that you can see in any unstructured mesh. As I mentioned before, these are the faces, and each face can consist of 3 or more, up to a maximum number of nodes. So in this case, we have an hexagonal unstructured grid, and our faces are hexagons, and our face-to-node connectivities are these nodes per each face. In any unstructured mesh, you can have differently than Xarray, data, face-centered data, node-centered data, or edge-centered data. So in this case, for example, if you are looking at a face-centered data, you can see something like this. If you have your faces like this, and you should be having your data values centered at the A, B, and C location. But if you have your data instead not centered, then you should be having your data values centered on these node locations. And because of some different applications, you may be needing to switch from data that is face-centered to node-centered, or vice versa, or analysis operations between these kind of different centered data. And likewise, you can also have your edges between each pair of nodes, and because of that, you can have edge-centered data as well. And identifying data mappings within the UXarray is as simple as just checking the dimensionality of the data array. If you have a data array in the dimensions of your face to nodes, or node to edge, or edge to node dimensionality, you can see your data is either face-centered, node-centered, and edge-centered. So after this, I'd like to turn back to the data structures, and I'd like to elaborate a bit on the slide we were talking about, how we are inheriting from Xarray data structures. As you may recall, we have said the grid object is where we are introducing the grid topology information into our corresponding data set and data array data structures. So grid topology information can have a lot of different information, from what are your nodes, what your faces are, and what is the connectivity between your geometrical elements like faces, nodes, and edges with the help of those connectivity data arrays. And grid data structure can have all of this information, as you can see here. So if you have a grid topology, you can simply open it with the help of an open grid function through the UXarray. We can give this a quick look when the code comes. So let me see if I can do that through the code. Yeah, actually we can, I think, give this a look from here. If you should have this. Importing UXarray is just like any other Python package. We tend to import UXarray as UX, and when we have UX as a package, we can start opening grids or opening data sets. One other functionality difference or workflow difference than Xarray would be in any unstructured grids analysis, you may have either multiple data files, one for grid topology definition and multiple others for data variables of interest, or if it is a small enough data file, you can have your grid topology information embedded into your grid data variable file as well. But in any case, you need to have a grid topology defined in your data file or a separate grid definition file. In this case, as you can see here, we have a grid definition file, and we also have a data variable file. At any point, if you would like to analyze your grid definition file, you can just open grid with the help of this ux.opengrid function, and you can investigate your grid. So just like you would do with the Xarray workflows, you could see some grid specific parameters like dimensions and coordinates. You can also see some topology related data variables such as grid connectivity information. you need to have what each of your grid elements like face, edge, and node have corresponding other geometric element in the connectivity information. And you can also investigate any grid topology related variable. Like in this case, these are the node longitudes, and this is the face node connectivity. In each row, you can see the faces, and each column gives you the corresponding nodes for that particular face. And you can see the interface is quite similar to UXarray because under the hood, these are nothing more than inherited UXarray objects. And likewise, with the UX dataset and UX data array, you can see any UX data variable of interest or dataset of interest with the help of open dataset, just like the UXarray counterpart in the same function name. And the dataset and data variable related items and data variables are very close to how you would see them with the UXarray. And you would be able to pick any data variable of interest from within a data set in the UXarray. And also the grid topology itself with the help of UX grid object can be accessed through any data set and data array. And this remarks, this is the counterpart of the data array. So this is the data array's grid topology, and we are just checking if their grid topology objects are the same, and they are supposed to be same. Let me check my time. I think we are going as expected. We are done with all of the introduction parts. We can now start looking into, Philip, are you there?
Yeah, can you hear me?
Okay, actually, yeah, we can jump into the methods and libraries for unstructured grids, but I'd like to take this as an opportunity, this transition as an opportunity to ask if we have any questions so far. Philip, I think we will have one question.
Yeah, so you touched on it a little bit. I think one of the challenges we run into working with unstructured grids is the convention not following a convention, and you have to figure it out yourself. So do you have a recommendation for how to work with those types of data sets?
Yeah, so what tools, first of all, are you using? UXarray or?
Yeah, using UXarray, and currently what we do is we open it in UXarray and then we inject the UGrid metadata before we work with it.
Okay, I see. And I think you are reading in data from like netcdf files, right?
Correct.
Okay. And as I mentioned, there are really plenty of grid formats in the UXarray. So that's really hard to recognize any data set, like just seeing the parameters. But at the same time, every single grid formats or grid model like MPass and ChemSE have some key required data variables that need to be residing in any netcdf file for that file to be recognized as that data model or grid model. And because of that, we are just implementing our data or grid model, grid format recognizer codes to rely on those kind of required parameters. So if we can find a number of required parameters, if not all, we can say, okay, this netcdf file is in this grid format. What I would suggest there, either you would use the UXarray to see what data format or grid format that particular netcdf file is sitting under, or if you are not going to be using UXarray, then you can at least check out the UXarray codes to see what required parameters. So if it was, for example, UGrid, I would like to say, go ahead and check out the UGrid Conventions webpage, because they are really making things clearly to give you a sense of, okay, these are the required set of parameters that I would be receiving from any netcdf file to say at least this is a UGrid file. So this is what we did. I don't know if Philip has anything to add on top of that, or if you have a follow-up question on that one.
No, that was good. Thanks.
Yeah, and again, please feel free to reach out to us, maybe through GitHub repositories or wherever you would like to, and we can bring the discussion forward from there.
Yeah, will
Yeah.
do.
Thank you so much. Any more questions?
This is a general capability thing, and I might be asking too much of UXarray. But I work in a river model that has hydrologic response units. It's an unstructured grid. The thing that's different about it is that the number of vertices is hundreds to thousands, and they don't.
For each phase, right?
Yes.
Yeah. Let me try to translate your definition at least.
Yeah,
You
sure.
didn't have a chance to ask your question, but at least definition. There might be huge sparsity in the connectivity information because of that. Like, you can have phases that is consisting of just 3 nodes, but also you can have phases that is consisting of 1,000 of nodes.
Yeah.
Is that a good understanding?
Yeah.
Yeah, okay. Yeah, go ahead with the
Very
question.
complex
Yeah.
code. Yeah. So we've had some problems with using tools like ESMF because these grids are so complex, they
Yeah.
don't necessarily perfectly align with each vertice doesn't, or each cell doesn't necessarily align with other
Yeah.
cells, so there tends to be lots of problems with the grid itself. Anyway, but I'm wondering if we have any hope of using UXarray.
Not
for the-
today, but
Not today,
not
okay.
today. Yeah, not today. Yeah, honestly.
Okay,
Yeah.
yeah,
This is a great question, and especially Philip and I and some other folks from the Project Raijin and Seeds partnership, the UXarray development team actually. We are just starting to look into these kind of, hey, how can we solve these kind of sparsity problems? So because this is huge, what we did so far, honestly and transparently, was there was much need for such a tool to at least uniformly, in a uniform manner, represent all of these scattered grid formats, and to provide people at least a set of usable functions for data analysis and visualization purposes. But we have had that sparsity problem in our minds, but we couldn't have a chance to look into that one. Instead, what we did was, your use case is, unfortunately for you, but fortunately for us, not the 90% of the use cases for other people.
Yeah.
So that's good news for us. And if we were aware of the fact that if we would be able to, put these kind of usable set of functions, that would be usable for probably 99% of the use cases for a lot of people.
right.
We are still aware of the fact that that 1% is a good sparsity problem and scalability and performance problem. We have participated in a hackathon in the early this year with the folks from NVIDIA, NOAA, NREL, and NCAR people as well. We just got the chance to, get started to look into these things.
Okay.
But for that one, from a development perspective, I think we need to learn more about how to represent sparse data arrays in scientific Python ecosystem. And I know people from UXarray, people from Dask are also looking into this and not yet to find a solution to, overcome and say, hey, we did this. Actually, sparse arrays are supported under UXarray with 100% confidence. There is no such thing like this. And yeah, I'm leaving the doors open that we will be looking into this, but at the same time,
Yeah.
that's a big problem.
Yeah.
Yeah.
Right. That's
What
I
we
thought,
did
yeah.
here transparently was, hey, most of the time we will have faces that would consist of 3, 4, 5, 6 in MPass, 7, okay,
Yeah.
8 or more, not very possible. We just, targeted at the,
Ah,
99%
Makes sense,
possible
yeah.
of things. Yeah.
yeah.
But
okay.
thank you so much for raising this question.
Yeah.
This is a wonderful question, and yeah, we are looking into this.
Okay.
And yeah,
Yeah. Thank you. Awesome.
any more questions?
I would just like to real quickly add with that. So
Sure, yeah. go
yeah,
ahead.
we've had like a couple requests from some ESMF people for similar, I think it was for like hydro basins with data sets that kind of have that same, those same characteristics that you described. So as Orhan mentioned, we're looking into just different ways of interpreting the UGrid conventions to support those types of heavily sparse data sets. So as of right now, yeah, it's not supported, but we are looking into implementations to hopefully eventually support it.
Yeah. Thank you so much, Philip. And any more questions from Zoom or the room? Looks like we are good for the time. Philip, why don't you go ahead and start with your sections?
Sure. Do you mind stopping your screen?
Yeah, I need to stop mine. Okay, go ahead.
Okay. This should be good. Just 1 second. Okay. And yeah, for anyone that's still virtual, I will have the chat open if anything pops up. So as Orhan already mentioned in his presentation for the introductory presentation, this figure right here is our UXarray plotting API. My screen is sharing fine, right?
Yeah.
Okay. So I'm not going to cover too much into the details of this design document right here, but I'll go over some of the libraries that we use. So we use the HoloViz stack of tools extensively throughout the design of our visualization functionality. And HoloViz is a collection of tools. So HoloViews, Data Shader, GeoViews, Spatial Pandas, and HVplot are all libraries that are part of this tool set. And they provide high-level functionality for visualizing different types of data sets within the scientific community. So think like Pandas data frames, UXarray data sets, really the heavily used data formats within the community. And some of the main advantages of it, especially through Data Shader, is that it's there's scalable implementations with Numba in the backend using Dask to have high performance visualization capabilities. So even if you're working with millions or hundreds of millions of data points, it's meant to be a way that you can quickly visualize them without needing to wait hours, minutes, however long a like matplotlib plot would take. And that's the main motivation why we wrote our package around it, because of the complexity and high throughput of data that's encountered with unstructured grids. So HoloViews, let's see. So HoloViews has several different collections of geometric classes that are used for representing different objects. So there's paths, points, polygons. As we covered in the data mapping section, we represent different geometries of our unstructured grid using these objects. And then with HoloViews, we can communicate with Data Shader and GeoViews to generate plots. GeoViews specifically is of interest because for anyone here that's used CartoPy before for geographic projections or for having different features on your plot, GeoViews is an equivalent for that within this ecosystem of tools. Spatial Pandas is a library that we use for their high performance implementation of a geodata frame for storing our representation of an unstructured grid for visualization. So we'll get to that in the polygon section. And lastly, Matplotlib. We know Matplotlib is extremely popular with everyone in research in the geoscience community. So we do have some very limited support for some of their functionality. The line collection and poly collection are two to name. And the main motivation for not using these is that the performance is not as good as Data Shader and the rest of the HoloViz stack. So while we do have support for the collections here, it's not our extensively supported one. And lastly, CartoPy, as I already mentioned, with GeoViews, it's used for geographic projections, having different features on your plot. It's almost a requirement for a lot of people that make visualizations within geoscience. And moving on to rendering techniques. So this is where things kind of get interesting, especially for folks with more of a technical background. A lot of times when you're making plots, you don't really think about what is happening in the back end, like what technique is being used for generating that data. But when it comes to unstructured grids, this choice of technique is extremely important because going into it blind without knowing which one you're using, you may be sitting for minutes or hours waiting for a plot to generate when in reality, if you would have swapped one setting, you would have had plots in seconds. And this leads to the first type of method, which is vector or shape geometries for plotting. So a vector image, really, however you may think of it, is just representing some sort of geometry exactly as it is mathematically represented. So for the case of a polygon, this would be you represent it in terms of its edges, you connect those edges together, and then you shade in the values between them. And yeah, so in UXarray, that would be how you convert a face into a polygon. And another example of this would be when you're plotting continents. These are usually stored as vector geometries, which are then overlaid on top of whatever plot you have. So this is actually coastlines, not continents, I believe. But to kind of highlight these different geometries, I have an example from the Shapely library, which Shapely is a extremely popular geometric manipulation library for storing and representing different geometries. And to highlight what we already covered in the unstructured grid overview, you can have points, which this might be a little bit small. Let me zoom in a little bit. You can have a single point, which is represented as a latitude and longitude pair. You can have an edge, path, or arc, depending on how you want to define it, which is a pair of points, each of which, as we know, is a pair of latitude and longitude points or coordinates. And lastly, you can have a face or a polygon, which is stored as a collection of points in a counterclockwise orientation that are closed within itself. So we can see the starting point and the end point are the same, which means that it closes back on itself. So these would be example of just very basic vector or geometric representations of different geometries. And rasterization is the technique that we utilize a lot throughout this cookbook, which is used for achieving acceptable and even very good performance with kilometer scale grids, which is in the scope of millions of faces and nodes. So rasterization is where we take these geometries that I described here, and we map them and bin them onto a structured fixed size matrix. So this kind of sounds like regridding for anyone that maybe is experienced with that, but this only happens at the visualization step. So there's no need for the user to worry about creating a new netCDF, loading it back in and rewriting their workflow. This is all handled by Datashader at the visualization step. And we can see here how points, lines, and polygons, the outlined black ones are the vector representation, and the gray shaded values in the back are what the rasterized versions would look. So for unstructured grids, for the case of MPass, the outlines in black here are the vector polygons, and you can see the jagged edges around it. That's the rasterized example. So for many applications, especially for visualizations where the quality isn't the number one goal, just for getting quick visualizations, this is a method that is highly encouraged, and we will cover that much more into detail when we get to the polygon and point section. But I will pass it back to Orhan, but if there's any questions, I'll do like a minute right here before we move on.
Thank you, Philip. Any questions? Yeah, go ahead.
Yeah, I'm sorry, not a question, but just want to mention that we do have in the schedule the break in 3 minutes, just to make sure.
Yeah, I think we are at a great time for that one. We can just start the break now and
But if there are any questions, I don't want to shut
Yeah.
that down either.
okay,
So.
yeah. Any questions?
Maybe I will ask one since I
Yeah,
have the mic
sure.
anyway.
Yeah.
Kind of going back to early in the presentation, you had mentioned the various things that you all were doing to engender the community and get the community involved, and also sort of, I guess, co-design UXarray with community input. Obviously, a big part of the emphasis here is making it very familiar to Xarray users on, who are working with structured grids. Have you run into situations where the necessities, the design necessities to support the unstructured grid sort of conflict with having that easy on-ramp for regular Xarray users?
Yeah, I can
Uh,
answer that one.
Yeah, go ahead. And
Yes, I don't want to go too much into that question because I have a whole talk dedicated to this on Thursday. But to answer your question, yeah, we've encountered a couple roadblocks. The biggest challenge though is there's some functionality like indexing or selecting selecting different elements, which mean completely different things in structured or unstructured world. So while someone may think the native Xarray functionality might just work, it actually didn't and would just give garbage results to the user. So one of our biggest challenges has been figuring out what operators and functionality to overload and which ones to like wrap or slightly change to make sure that there's none of that confusion or none of those roadblocks that the user encounters. Does that answer your question?
Yeah, thanks. And it sounds like I'll learn more at the talk, so appreciate that.
Yep. Thank you.
Another thing was not a roadblocker or like barrier, but something to consider was through the community discussions, being as close as possible to Xarray was, I think, the strongest expectation from the UXarray potential users. And to satisfy that, we ended up actually inheriting from Xarray. And people who know Xarray and Xarray documentation and maybe are in touch with Xarray developers may have right away noticed inheritance from Xarray is not a thing that they recommend you to do as the Xarray developers. They actually recommend to use their accessors rather than inheriting, because Xarray internals are huge, and when you are inheriting from them, you are kind of taking the risk of future big code changes, So, but again, we have had a lot of discussions with the core Xarray developers on that one, and based on our structure of UXarray and the functionality and the design and architectural expectations, I think we were convinced with those people that inheritance would still be a path to explore. So far, it's going great, and it's giving us, and in the second part of the tutorial, I would like to touch a bit into those parts as well. So far, it's giving us a lot of convenience, such as providing our own UXarray visualization functions, but at the same time, keeping the compatibility with Xarray's native visualization functions as well. So, and that gives us an opportunity to seamlessly provide the end user with the functions from UXarray we are providing them with, but at the same time, the functions, they are natively coming from Xarray. That's great. In the future, there is a risk of, if they change the Xarray API drastically, we will probably need to, take some, break and to our UXarray implementation and look into those changes and how to satisfy them in the UXarray. But that was a risk, and that was kind of a decision making with the design choices. And then there is no, one size fits all kind of situations here. So anyway, so that was a good question, and I think there are gonna be some parts that we will need to probably discuss again in the second section of this tutorial. So thank you. Any more questions before the break? Anything from the Zoom chat, Philip?
Nothing that I can see.
Okay, so let's not take any more of the break. So it is 2:33. We are hoping to see you all back 3 p.m. Okay, great. Thank you. Okay, so it's 3 p.m. I think we can get started with the second part of tutorial. Paul, can I screen share now? I disconnected from Zoom in the meantime, so let me just get connected again. Okay. This is the correct place we had left. So far we have covered these two sections of the cookbook we had been using, and this is the final section we will be covering in the rest of today, which will be an actual dive into the visualization functions while we are still maybe connecting to why we did some of those decisions, made some of those decisions for software engineering purposes. Before everything, I would like to elaborate a little bit on more on this UXarray plotting API and how it's been helpful for us to provide user API functions in the visualization sets. Let me zoom into this a little bit more. Is it readable? Something like this. Okay, I think I had already mentioned this through the slides, but I'd like to emphasize one more time. Our visualization functions are wrapping up the functionality from HoloViz stack as Philip described in the previous section. What we mean by that is under the hood, there is actually the HoloViz stack functions executing, but we are wrapping up them in a way to support in a more convenient way unstructured grid visualization with all of those parameters and things like that, and the functionality names as well. Give me just a few seconds. I'm struggling to find. I think I just closed that tab. Okay. Yeah. That's one thing. Another thing is, as we said, we are actually inheriting from not for this HoloViz, but in general from the UXarray design. We are able to provide our UXarray users with not only the UXarray related visualization functions, but also the XArray dot plot native functions. For example, if you would like to plot any grid topology function, you would be needing to call one of these functions. But if you would like to use any native XArray functionalities, such as you would like to maybe just have a quick look into the histograms of your data, you can still do that seamlessly. You would still be doing the same thing like UXarray, your data array, and plot, and the method name. If you call the XArray native function names, you would be able to get them executed on your data array, or if you would like to have some actual UXarray functions being run and to give you some plots, you can also do that with the help of these functions. Another thing Philip had already mentioned, I would like to emphasize a little bit more. we rely on HoloViz stack packages, but at the same time, they are supporting still Matplotlib functions, Matplotlib plots with the help of their backend mechanism. So even though we are not directly providing Matplotlib functionalities for visualization, we are still providing our functions just with the convenience of a parameter called backend. If you pick your backend to be Matplotlib, you would still be getting Matplotlib plots, which I will be showing you in the rest of today, and Philip as well. I think that's enough about this API. We have covered all of these so far, the takeaways. I think, yeah, we can start looking into some of the codes. After an UXarray imports, as we mentioned before, most of the time, your use case or workflow looks like you are having a grid definition and you are having one or multiple data files depending on the use case. So, and with that grid definition, you don't always have to do this open grid. If you are explicitly trying to diagnose your grid topology, you may be needing to open grid, but other than that, most of the time you should be good with just opening a data set and accessing the grid object through that data set with the help of uxdataset.uxgrid or uxdataarray.uxgrid. We had covered this grid topology details before, the dimensionality parameters and coordinates as well, coordinates in the Cartesian format and connectivity information. And this is something so different than the structured grids. With any unstructured grids, you may have one or multiple connectivity data arrays, and with the UXarray, we are able to generate all of those connectivity information if we have just one of them. For example, face to node. If we have face to node, we can also generate node to face and the other connectivity information. Here, yeah, most of the time, the scientist workflow would rely on this API function being called, opening the dataset, just like they do with the X-ray counterpart. And as a result, they would have a UX dataset instead of an XArray dataset, but which would resemble XArray dataset very much. As you can see here, it is still coming from the XArray package because of the inheritance between UXarray and XArray, but it is giving you the end result as the UX dataset rather than an actual XArray native dataset. And because of this UX dataset, you have some helpful additional parameters like the UX grid and other things. Let's have a quick look into how the grid plotting would look like, even though we have some other sections that are directly dedicated to the grid topology plotting. So if you were going to plot some grid topology information, you would be dealing with a grid object. In this case, this is the actual standalone grid because of the result of open grid function call. If you have such a grid object, you would be just calling grid.plot as the default plotting method, or you would be calling something through the plotting accessor like this one. If you are interested in your plotting your nodes rather than the default visualization function, you would be calling like this: grid object dot plotting accessor dot plot dot nodes, or you will be doing similarly grid object dot plot. In this case, we are calling still the default function, but you would also be able to do that with the edges or mesh. In this use case, you can see rather than the standalone grid object, you have a UX dataset of interest through which you are first accessing the grid object This is the data set. This is the grid object, and this is the default plotting function. And as you can see with a lot of other high-level visualization packages, such as the HoloViz itself or maybe others, you can have a bunch of parameters that are specific to unstructured grids, or also we are providing the parameters that are coming from the internal HoloViz visualization functions. So as I mentioned before, you can play with the backends in between Matplotlib and Bokeh, and you can also play with your some plot related parameters like title and aspect ratio and the figure size as well. When you have the backend as the Matplotlib, you can see there is no interactivity here naturally. The only interactivity is coming from when you have the backend as Bokeh rather than Matplotlib, just like you could see here, for example. We will be looking into the details of them, so I wouldn't like to focus on the interactivity part. Maybe Philip or I can cover that one in the next parts of the tutorial. If you are interested in plotting some UX data array instead of the grid topology, you would be picking your data array from your data set like this. Then you would be accessing your default plotting method or any other plotting method of interest through the dot plot accessor. And in this case, we are plotting the bottom depth parameter name from this data set. And this is, I think this should be a quick rasterization visualization. Again, we will be looking into those details of the rendering techniques in the upcoming parts. I wouldn't go into details of those in this one. This is just for giving you an idea of how you could plot grid object itself, UX data array, or any data array of UX dataset. For UX datasets, as of today, we don't have any plotting functions because most of the time you are plotting your data array of interest rather than the dataset. Maybe in the future we might have some functions here. Again, if you were interested in, for example, this one, interested in some XArray native visualization functions on any of UX data arrays, you would be calling them like this: UX dataset and your data array of interest or variable of interest, dot plot accessor. Then instead of the UX array function, you would be calling here the native XArray function. For example, if you are interested in plotting the histograms, you could call histograms here, and under the hood of UXarray, we would be seamlessly providing that function through the XArray namespace, and you wouldn't even see any difference between UXarray or XArray function calls other than the actual result of the plotting.
And if I can just add something real quick.
Please
So
go
what
ahead,
Orhan,
yeah.
what Orhan mentioned, that's it's currently in review, that functionality. So in the next release, we should have native XArray support. But as of right now, if you were to install the package, it's not in our latest release as of right now.
Yeah, thank you so much, Philip, for that one. And actually, this brings us to your part, comparison to XArray. And before Philip, I would like to add one more thing here, like comparison to XArray and this cookbook in its entirety and other like user guides and usage examples. These are all for the purpose we mentioned in the beginning of the tutorial, like to give a better understanding of what UXarray is trying to do besides XArray. And because of that, this notebook is here. Philip, would you like to take it away? Actually, I can help you with the presentation because we will be switching back to me just in a few minutes. So just let me know how you would like to proceed.
You can go along and present it if you want. If anything, I can interject, but it's a pretty short notebook, so you should be good.
Okay, let me do this. Thank you so much. This is again an end user focused notebook. which tells people how you would run or implement any workflow that you would do in Xarray similarly, but at the same time with the help of some like different functions in the UXarray. So that hence the name is the comparison to UXarray. So if you are a person coming from the Xarray backgrounds, so it will be a great notebook, a reference notebook to look into to see what are the differences, what are the resembling as well. And Xarray and UXarray related imports would look something like this. UXarray importing here and Xarray is there, and Matplotlib would be imported for Xarray purposes, as you would do for many plotting use cases. And then there might be some keyword arguments for the plotting, just for the convenience purposes. Backend to be Matplotlib and aspect ratio and figure size. We talk about a lot of times about the data. So a structured grid would be only a data file for the data variable itself, the data variable of interest, like here. And a plotting scheme with Xarray would look like you would first open data set with the Xarray, then it would give you an Xarray data set in return. This is what we were talking about, the Xarray data set coordinates and dimensions, and the data variable, it's present there. Then that's it. So at this point, we have an Xarray data set, and how the things would look like in the unstructured grids is instead like this. Everything similar, but as we mentioned before several times, we have an additional grid definition file because we need to know what is the unstructured grid topology looking like. And because of that, we have this grid file, and you would still do a very similar open data set, but now with the UXarray package. And in that case, you would be feeding your open dataset function with first the grid definition file, then the data file or multiple data files of interest. At the end, just like the Xarray case, you would have an UXarray dataset, which would be really similar to your Xarray counterpart. Dimensions, coordinates, and data variables present there. And when it comes to plotting, the things would look really similar as well. In most of the time, you would have a data variable of interest in your data set like this. You would be selecting that one from the data set. Then you would be accessing your default plotting method like this. And it would give you just a single plot, or if you were interested in a figure with subplots, it would look something like this in the Xarray. With the help of Matplotlib subplots function, you would be creating a subplot figure with subplots first, then plotting your Xarray data variables there with the help of these two. And in return, you would have a Matplotlib collections quad mesh object, which would give you a figure with two subplots. When it comes to UXarray, most of the things would be really similar to Xarray counterpart. You would be picking first a data variable of interest, then plotting that one with the default method like this. Or if you were interested in a figure with subplots, likewise to Xarray, you would do something like this. Because we are wrapping up on top of HoloViz functionality, it would be as simple as you generate a plot, then you add another plot into your existing plot. This is the first plot. This is a high-level addition between two figure objects, and at the end, you would have a figure with the subplot opportunities. This is everything using HVplot to combine. Philip, maybe you could help me recall this one again.
Yeah, so this one, as we saw with those two previous sections, you can't, so since UXarray uses hollow views and Xarray uses matplotlib as their backends, you can't seamlessly integrate both plots together into like a single subplot. But one thing you can use is the hvplot library, which I already mentioned this in the plotting library section. But this allows you to have an additional accessor that is accessed through an Xarray dataset, which lets you combine and pair UXarray plots with Xarray. Another added benefit is this also makes Xarray plots interactive. So if you want to zoom in to that Xarray implementation, Orhan, you can see that you have that same level of interactivity that you would with the UXarray native plots, but this is directly on the Xarray object. So this right here is just an example of how to link them both together. It's an extra step than what you would do just with native Xarray plotting, but it's really just using a different import and calling a different plotting method on Xarray.
Yeah, thank you so much, Philip, for this one.
Yeah.
And I think it wraps up everything about this comparison to Xarray notebook, right?
Yes.
Yeah, okay. Any questions so far? Not for the times. Okay, let's move on to the next topic, which is the grid topology. Now we can look into details of why grid topology visualization would be needed. So in unstructured grids, actually the grid topology itself is the geometric information that your data is residing into. And because of that, at any time throughout your workflow, data analysis or visualization, regardless of what it is, you may need to diagnose your grid topology to make sure about the geometric elements and whatnot. And because of this, UXarray provides a bunch of visualization functions for only grid topology plotting purposes. I think we would just skip these parts as we mentioned several times now, like grid file and the data file we are opening here. Then we are opening them as an open data set like this. At the end, we have an UX data set. And this is important. As you can see, there are a number of ways to visualize a grid object in the UXarray. If you have a standalone grid object like this, you can do call plotting functions like this. Or if you have a data set or data array, you have to first access your grid object through the data set or data array through this UXGrid object. Then you would still be able to run your plotting functions through the plot accessor. At any time, you may need to plot edge, node, or face is going to be covered in the next section, but edges or nodes to make sure about your grid topology. And plotting edges is actually the default plotting function of the grid object. Even if you didn't call any dot plot accessor through your grid object, you can call the default function like this, and you can get your grid visualized. And there are some like performance optimizations or performance discussion here that we can take. So in any unstructured grids, you may have faces that are passing over the antimeridian, and if you would like to get them plotted in your plot or not, you can make use of this exclude antimeridian. With some huge data sets, this would be really a game changer for the performance purposes if you excluded the antimeridian. So it depends on your use case and what you would like to see at the end of the plotting. So in this case, the antimeridian faces are excluded, and as you can see here, those were going to be here are gotten rid of. And what else? We talked about this already, but if you specify your backend to be matplotlib, you can get your plots in a matplotlib object. If you didn't specify anything, we default that one to bokeh with these interactivity features. And plotting nodes is similar. So at any time, if you access through your plotting accessor, then the nodes function, you should be able to see your nodes in a similar fashion for your grid topology visualization. Face and edge centers. As you may recall from the first part of the tutorial, we were talking about data mapping. So your data would be either data centered on faces or edges or nodes. And because of that data mapping, you might be wanting to plot your data at the face centers, node centers, and edge centers to see how things are looking with them. And there are some function aliases as well to call the same functionality in different names. And we are also documenting them here in the tutorial. And because of the HoloViz stack's high-level capabilities, you can at any time combine your plots into a single one. For example, if you would like to see all together your nodes, edges, and centers of them, you can just create your plots and just combine them with the asterisk symbol in the HoloViz terminology, and you can have a combined visual of your individual plots. This wraps up the grid topology visualization, and now Philip is going to be covering the polygons.
Thank you, Orhan.
Sure. Let me stop my screen sharing, Philip, and you can take it over.
Sure. Okay, is my screen good?
Yes.
Okay, so I know we've already covered a lot with plotting. We've showcased multiple different methods, multiple different ways of calling them through our core data structures. These next two notebooks that I'll be covering go into some of the details of how we've implemented certain visualization methods. So the first one here that I'll be covering is our polygon plotting. And as Orhan has already mentioned, unstructured grids are used for representing complex and irregular geometries. And these geometries are stored internally in terms of connectivity information and coordinates. And in UXarray, we can manipulate those variables to natively render and visualize the unstructured grid by representing the data as polygons. So I'll skip the setup again. We've had this multiple times already. So the first type of plot that we have is a vector polygon plot. So as we already know, vectors are exact representations of the geometries plotted onto rendered through our UXarray functionality. So to access vector polygon plots, it's called through the uxdataarray.plot.polygons. And as we can see here, we're using by default matplotlib. So this plot isn't interactive, but by using Bokeh as our backend for the interactive plots, we can investigate a couple things. So here, if we hover over a face, we can see the data value that is mapped to it. So this cell right here has a value of 5053. Zooming around, you can see all of the data values right here. The next thing is, as we do zoom in, you can see that there's no apparent drop in visual quality for the data. So you can zoom in as far as you want, and the data looks exactly the same as it is from a global perspective. And if we do zoom in again, we can see the clear and crisp edges that make up each polygon. So like if you were to zoom in as much as you can, it's still just the intersection between the edges right there. And yeah, just to summarize that with the static plot right here, vector polygon plots offer some of the highest level of data fidelity that you can from our visualization stack. When I refer to data fidelity, I mean that there's no loss of quality when you zoom in, and the accuracy is exactly what the data is within the data array. So there's no questions, you know exactly what you're looking at. However, as I'll get to in a little bit, you maybe don't always want to plot using the vector method. So we also support rasterization of those polygons, and that's called through the .plot.rasterize method. And you specifically need to select what type of rasterization you're doing. In our case, we're rasterizing the polygons. And just looking at it at a global perspective, it probably doesn't look very different for those of you that are in person. But if we go into our interactive example, the first thing that we do with these raster plots is if we zoom in, if we look here at the Gulf of Mexico, so right off the bat, when we zoom in right here, you can see how heavily pixelated it is. If we zoom in even further, it really doesn't look like an unstructured grid anymore. It looks like a structured one. And that is part of the benefit of rasterization, is that you essentially are regridding at the visualization step only for rendering. You're not actually modifying any of your data that's stored in the data set or data array. This is all just done very efficiently through data shader at the visualization step. One other thing though is if we do hover over the data, it's still like the 5053 cell that I mentioned earlier. It's still the same data. The primary difference though is the boundaries aren't as nicely defined as they are with vector plots. And that's expected because we're just working with a fixed cell size and a fixed number of cells in each X and Y direction for rasterization. So you don't have as many pixels to represent your geometry. And to kind of summarize that with the data fidelity is like if we restrict our view to that region right there, you can see that even though your data is still the same values that are stored in your data array, the boundaries aren't clear and it's an approximation of the geometries by using rasterization. But there is something you can do to make these plots look better. And you can specify a value called a pixel ratio. The pixel ratio, at a high level, what it does is it's increasing the pixel ratio makes each bin, so you have more pixels for your overall image. So this means that a high pixel ratio will give you a higher effective resolution and a better approximation of the vector plot. And on the contrary, a low pixel ratio makes each bin larger, so you have larger pixels in your overall image. And this can be highlighted right here in this subplot. We have a 0.5, which is considered a low pixel ratio, and then you have an 8.0 high pixel ratio. And we can see this 8.0 one looks very close to a vector polygon plot, but you can still probably observe some of the edges, the jagginess associated with the edges. So kind of to summarize the pixel ratio, choosing a higher one is usually suggested when you're going to be zooming into specific regions of your plot, because you would want to have a slightly higher data fidelity compared to just the blockiness here, which you kind of lose the sense of working with an unstructured grid. And Orhan already mentioned this a little bit, but we handle polygons around the anti-meridian using the anti-meridian package, which documentation is here for anyone interested. But the reason for this is that most of the unstructured grids that we encounter are from global climate models, meaning that they cover the entire globe. And geometries on a sphere they don't translate exactly to a 2D plane. So there's some cycles that happen across the anti-meridian, meaning that polygons want to connect to the other side of the plane when we're in a 2D geometry, which causes artifacts across the globe. So with UXarray, when you choose to set exclude anti-meridian to false, this performs some additional data processing at the visualization step to allow you to perfectly split polygons across the anti-meridian. So we can see here to the left and right of the anti-meridian, there's a clear boundary which represents where they would have connected. And while this looks really great visually, it is about a 4 times performance hit in terms of the overall execution time for processing the data. So it is a non-significant amount of time you would have to put aside to allow this processing to happen. So what we've included just for generating quicker plots is if you set exclude anti-meridian to true, we simply just remove those data, those faces from the output of our grid. And for the case of like a high resolution million face grid, it's less than 1%, usually like a fraction of 1% of the overall faces that you lose. And because at that resolution, the faces are so large or so small, you don't really notice them missing from the overall data. So for here, we can see that to the left and right of it, we simply just excluded them, and this is because of performance. The next thing is, I've already mentioned this before, but projections are extremely important for a lot of workflows with researchers. And supporting projections has been one of our blockers that we had with these polygon supports. The main reason was we want to make sure that our performance is as high as possible, since our goal is to support kilometer scale grids with efficient plotting routines. And some of the additional steps we needed to support projections and other features would have slowed down our performance significantly. But there is some silver lining. So because we're written to support the HoloViz stack of tools, we already support Spatial Panda's conversions directly. So by calling the toGeoDataFrame method right here, we can actually access the geodata which is used to generate all of these plots internally. So we expose that functionality to the user in case they want to use native HoloViz data shader, any other HoloViz tools through this object right here. And what we can do, once we've exposed that geodata frame, you can actually use HVplot, which Orhan covered in the comparison to UXarray section, to directly plot through the geodata frame. So we can see here a couple examples of what you can achieve with this. I will just say right off the bat, for high resolution grids, the performance is significantly worse than our native UXarray or UXarray functionality, but for small to medium grids, there's really no issues with this. So we can see here a Robinson projection, and this is achieved by simply calling very similar, almost exactly the same parameters that you would with UXarray, but you pass through a projection using CartoPy. So we can see here the Robinson. You can also shift the center of your longitude or latitude. So here we've centered it across the anti-meridian. This is especially important for anyone doing research in the Pacific Ocean. You would want to center your data over that. So with GeoViews, so I did mention CartoPy, but GeoViews allows you to add different features to your polygon plots. So you can see here, we're adding the coastlines and the borders, and we're using that same Robinson projection centered across the anti-meridian. And lastly, I always like these examples. I always like orthographic plots, but here's an example of using an orthographic projection centered across the North Pole. So if you're doing any analysis with sea ice in the North Pole, or if it's just your region of interest, you can use GeoViews paired with HVplot to reproject your data to generate plots like this. And just a couple takeaways before I move on to the next one. So polygon plotting is our flagship method. It's the one that achieves the highest level of data fidelity and has a large number of customization options. And we strongly suggest rasterization for most applications, especially if you're working really with any grids more than a few 100,000 elements. It's the performance improvement that you get from it is, in my opinion, always worth the slight loss of quality. But vector plots should be used mostly when working with small grids, or when you want as high of quality in your plot as possible. And when should you set anti-meridian to false? We almost always suggest you keep it set to true, meaning that you exclude them, just because the performance increase and losing a small number of elements is not really that noticeable for large grids. But when you're working with small grids, especially some of the other ones that we've covered in this notebook already, it's suggested to keep it to false, because for small grids, you can't tell there's a performance difference, and it's much noticeable when a large polygon is excluded as opposed to a tiny one. So it depends on your use case, but these are just a couple options. I'll move on to the points, and then I'll take questions.
Any questions? Philip, looks like we are good to
section
go.
before.
Yeah.
Okay, so I just covered the polygon plotting. Another one of our visualization methods is point plotting. So we know that our unstructured grid is composed of nodes, edges, and faces. But in addition to those elements, the edges and faces can also be represented using points in terms of their center coordinates. So by using those coordinates, we can represent them as points and shade them to have an alternative way to visualize data. So again, the setup here is mostly the same. I will mention though, we have two different grids here. We have a 120 kilometer and a 480 kilometer. We'll see that later on how the resolution plays a big role in when you can use point plots. But when we want to represent coordinates as points, for 2D visualizations, you can just shade pairs of latitude and longitude coordinates as points. And there's three types of coordinates that UXarray supports. There's node longitude and node latitude, which this is used for representing the latitude longitude of the corner nodes, which that is used for node-centered data. We have the edge longitude and edge latitude, which this is the center of each edge. And this is used for shading edge-centered data. And just as a background, they can be derived from the node longitude and node latitude internally by using some Cartesian averaging that we have written. And lastly, the face latitude, face longitude, it's just the center of each face represented as a latitude longitude pair. And this is used for when you have face-centered data. And all of this right here leads us to the vector point plot. So a vector point is just where you plot your point exactly on the grid. So as you zoom in, we can take a look. Each point is exactly the same size that you have. So just dynamically looking around the grid, we can see that if we were to plot the edges around here, you see that these are the face centers of each point. And they're shaded using the bottom depth variable. So we know that bottom depth is a face-centered variable, meaning that when we plot the points, it's plotted alongside the centers of each face. And you can increase the size of each point by setting a size parameter. So we can see here that each point is larger. And with points, UXarray does support native projections because projecting points is much simpler than projecting the entire connectivity of the grid. So you can actually, as we had with the previous example, just pass through a CartoPy projection. And this allows you to natively project your points into whatever projection you want. So those were vector plots. The next one that we have is our rasterized point plots. So they're called through .plot.rasterize, like was the case with polygons, but you set your method as point. So instead of polygon, you set point as your method. And when we compare the raster here for the 480 and 120 kilometer grid, you can start to observe a couple trends. So we can see that, which is expected for the 120 kilometer grid, there is a much higher density of points, and the rasterization, it almost just looks like a staticky representation of what the global trend looks like for the data. So remember, if I maybe just real quickly go back to the polygon section as a reference, this is roughly what the data should look like. But when we look here, it's a very faint outline of the entire data variable. And you can actually specify a pixel ratio value here, which the definition of the pixel ratio here is the same as was with the polygon plot. It's just the size of each pixel. So having a high pixel ratio means you have very small pixels that can catch much fewer elements. So with that, we can look at two drastic examples. So for our point raster with a 0.4 pixel ratio, you can start to see the global trends here of the data variable. Going back here just as a reference, this is what the polygon one looks like, and this is what our point raster looks like. So at least near the equator, as you go further from the equator, there's some interesting behavior, which I'll touch on, but here it looks pretty good. But choosing a 2.0 pixel ratio, it looks significantly worse. And the reason for this is when you choose so you would actually want to choose a low pixel ratio in this case, because each pixel is then larger, which can cover a larger surface area of our entire plot, meaning that there's a high likelihood one of these points here falls into that region. And that's fundamentally what rasterization is doing. It's just grouping and binning these points to generate a plot. So one of the trends that we noticed, though, is near the poles. So remember, this data is from a climate model. So it's, even though it's evenly distributed across the sphere, this 2D projection here, I think it's a Mercator projection or one of those, there's a much lower density of points when you go towards the poles. And this can be alleviated by using a projection that better distributes the points. So I'm not a big fan of this projection, but it's good for this example. Using the sinusoidal projection, we can see here that when we zoom into the poles now, the points are much better distributed across the entire globe. So you don't have those missing values that you have down here. And so this is a 120 kilometer grid. So I think off the top of my head, it's about 50,000 nodes, which isn't a lot, but it's also not like a tiny amount. I want to show a high resolution example here, which we'll cover a little more at the visualization at scale section. But this is taken of a 3.75 kilometer MPass mesh. And so that's roughly 42 million faces and 84 million nodes. And this is a point raster right here. And you can see it looks really, really good for the most part. You still have those issues near the poles where there's a lower density of points. So the rasterization starts to fall apart. But if you transform this, so this plot's so big, I need to zoom out a little bit. But if you transform it into a orthographic projection, you really can't tell that there's anything wrong with this data. It actually looks really good. And the main benefit of point rasterization, I'll cover it more in the next section, but these types of plots can be generated in seconds as opposed to minutes with some of the polygon plots. So there's a significant improvement in performance. And just a couple takeaways before I move on to the final one. We suggest using raster point plots with an appropriate pixel ratio and projection when you're working with roughly medium to high resolution grids. Otherwise, vector point plots can be used sparingly. Really, there's not much information that you get from looking at data this way. One example could be if you overlaid on top of like a polygon plot, you can represent multiple data variables on the same plot. But again, that's like a very edge case, and we mostly don't suggest using the vector plot unless you have an application that can benefit from it. So I'm going to move on. I'll save questions for the end. I see we have about 10 minutes left. I'll go over the visualization at scale. So just a couple benchmarks that we ran on a single derecho node. We benchmarked, so that data set that I showed you, the high resolution MPass one, we had 4 variants of it, a 30 kilometer, 15, 7.5, and 3.75 kilometer variant of it. And at the extreme, it's 42 million faces and 84 million nodes, which is a lot of data that you're working with. And everything here was run on derecho. These timings are from around Christmas time. So we need to probably run some new benchmarks, but there hasn't been many changes to our functionality. But for the 3.75 kilometer, if you include the anti-meridian, it takes about 2,000 seconds, which that's a long time to wait just for a single plot. If you exclude the anti-meridian, it actually brings it down to just 93 seconds for the data processing. So that's about a 20 times decrease right there in overall performance. But if you look at the point raster, it blows everything out of the water. It's 1 second for data processing. And because of that, so this was the initial run. And internally within UXarray, we do some caching. So once you've created your geodata frame that's used for the polygon raster, you're actually able to reuse it. So you don't need to continuously run these expensive computations because we use the cached variant of it. The only time you need to recompute it is when you switch unstructured grids. So most of the time when you're in UXarray, you're always working with the same unstructured grid that's linked to each object. So there's you can utilize this cached behavior. And for subsequent runs, so here we can see that it takes about 14 seconds afterwards to generate the highest resolution plot. And this is just some overhead with Jupyter notebooks and actually getting the plot rendered. And we can see that with the point raster, it's the same because we don't cache it, but it's so quick that we don't need to. And let's see. Couple comparisons of that same plot that I had. So here we have a global polygon raster of that same data variable for the 3.75 kilometer mesh. So we can see here, it looks great. And then also near the poles, there's none of that weird behavior. Looking at the point raster, we can start to see near the poles, just because of the curvature of the Earth and the density of points distributed, there's some missing values. But if we zoom in, so there's a very small region here between -50 and -100 longitude. I'm not sure if you can see my cursor, but if we zoom into that with the regional polygon raster and then compare it to the point raster, they look exactly the same. And as we saw with the polygon example, you would need to use a different pixel ratio. However, with polygon plots, there's some functionality that we didn't get to cover called dynamic rasterization. So when you set dynamic to true with a polygon plot, it re-rasterizes when you zoom in. So I'm going to jump into just a Jupyter lab right here. And I want to show you what that functionality looks like on this data set. So this is one of the lower resolution ones that we had. But if I zoom into the Gulf of Mexico with dynamic set to true, you can see that each cell actually gets re-rasterized. And zooming in as close as you can, you really can't tell that it's different from a vector one, from a vector plot. And this happens globally. So I can go in and zoom over the Baltic Sea, for example, and there's a lot of missing values here. But you can still see that the rasterization is occurring on the zoom in step. And this is on my local machine, which it's no crazy machine. It's like 32 gigs of RAM with an i7. So even on like my machine, this rasterization is insanely quick. And that's because of Data Shader and Spatial Panda's use of Numba internally. And that it can take advantage of Dask clusters as well, but we've had some issues with that. But this is what the dynamic one looks like. And going back to the visualization at scale, this is the dynamic polygon. And if we set dynamic for points, we lose the whole benefit of having a polygon raster because it starts to render each point individually now. And because of that, you can't really tell anything from this graph. So even though with that, when it sets to dynamic equals false, they look exactly the same. This is what the data actually looks like on zoom in. And the nice thing with the polygon raster is you can zoom in even further up to the point where you start to see each individual cell. So you can even see here, looking at the longitude, this is the whole longitude on the bottom. That's about a 1 degree delta. So this is a 1 degree by 1 degree, roughly 1 degree by 1 degree box that we're looking at right here. And this is how many polygons there is within there. And that sums everything up from this notebook. Yeah, there's a little bit extra text in here for someone that may be more interested in some of the details, but I think that wraps it up for today. We've got exactly 5 minutes for questions, so doesn't look like there's anything online. Orhan, is there anything in person?
Thank you very much, Philip, for your section. And let me ask, do we have any questions? We have one at least.
Say get imagery out in front of a web map tiling service, where would you recommend that I could like plug into the work that you've already done?
So the question cut off for me online. Can you repeat the first half of it? Sorry.
Yeah, I think the mic wasn't correctly working. So if I want to create a web map tiling service and just get imagery, you know, serve that to web clients, is where might I be able to plug in to the API?
I can possibly answer that one, Orhan. So with our functionality, it's all written with HoloViews, which HoloViews itself uses Boki as a backend, which I know you can, I think Boki is all JavaScript, and you can export the plots from there and embed them within web services and websites. I think there's also servers that you can set up with Boki and HoloViews that can have like some communication between the client and server for obtaining some like real-time rasterization of data. So UXarray, we don't re-implement the wheel with any of that, but we do most likely support integration within other HoloViews and HoloViz services. So does that answer your question?
Yeah, thank you.
Yep, thank you for the question.
When you say imagery, I don't think you mean shapefiles, right? So what is the data format? Still in the like NetCDF?
No, to in images like PNG.
Have you ever experienced HoloViz tools with imagery, Philip?
I mean, an image is you can consider an image as a raster, and I think there, off the top of my head, is ways of loading images and converting it within the HoloViz ecosystem, but I think HoloViz just treats images as a raster.
Okay. Thank you. Any other questions? Checking Zoom again one more time. Okay. Christina, thank you so much for your comment. No question here, but what a nice package and demo. Thanks so much. Any more questions? Okay, looks like we are tired. Yeah. Thank you so much. Hopefully it was a helpful, nice tutorial. And please feel free to reach out if you have any use cases or if you have any questions, or maybe from a developer's or end user's perspective, if you have any suggestions for us to improve, make better in the future. So we really appreciate these kind of opportunities to come together with the developers and end users, and this is great. Thanks so much. I'd like to thank Philip as well. Philip, thanks so much for your work here. And Brian, please feel free to take it away to wrap up today.
Thank you all.
Yeah, thanks, Orhan, and thanks, Philip. And thanks to everybody for, attending day 2. So that wraps us up for today. Hopefully the weather outside is all right for your rest of your day here. We'll start tomorrow, I believe, again at 9. And tomorrow we'll have some talks as well as a panel session at the end of the day where we'll talk a little bit about Jupyter Notebook proceedings and some of the thoughts we had for this year's conference and where we'd like to take that in the future. So yeah, I think if you want to follow up with Orhan or Philip on any material that they talked about today, or some of the Intel material earlier, we should have that contact information available. And yeah, otherwise, have a good rest of your day, and we'll see you tomorrow. Oh, yeah. Yeah, so I know that Tasia will send an email to all the participants with details on that. I'm not sure of the exact turnaround time, but as soon as we can. Yeah. Oh, and I guess the daily announcement that there's probably still some snacks out there. If you want to take a, to-go bag, go for it.